In the vast darkness of our universe, something lurks at the heart of nearly every large galaxy. Something so powerful, so massive, that it shapes the very fabric of space and time around it. These are supermassive black holes, the colossal beasts that reign at the centers of cosmic neighborhoods like our own Milky Way. They are the ultimate cosmic enigmas, objects of such extreme density and gravitational power that they challenge our understanding of physics itself. Imagine an object with the mass of several billion suns, compressed into a space smaller than our solar system. These cosmic monsters are so dense that nothing, not even light itself, can escape their gravitational pull once it crosses a boundary known as the event horizon. They are the ultimate cosmic predators, consuming stars, gas, dust, and perhaps even other black holes that wander too close. Yet despite their destructive potential, they also play a crucial role in creation, helping to shape the very galaxies they inhabit. The concept of black holes first emerged from the mathematical equations of Einstein's general relativity in the early 20th century. For decades, they remained theoretical constructs, mathematical curiosities that seemed too extreme to exist in the real universe. Even Einstein himself was skeptical that such objects could actually form in nature. Yet as our observations of the cosmos improved, evidence began to mount that these extraordinary objects weren't just mathematical abstractions. They were real cosmic entities lurking in the darkness of space. The journey to discovering supermassive black holes has been one of astronomy's greatest adventures, spanning more than a century of theoretical work, observational breakthroughs, and technological innovations. It's a story of human ingenuity and perseverance, of scientists pushing the boundaries of what we can observe and understand. And it's a story that continues to unfold today, as new technologies allow us to probe these cosmic beasts in ever greater detail. What makes these giants truly fascinating isn't just their enormous appetite or their mind-bending properties. It's the crucial role they play in the birth, life, and death of the galaxies they inhabit. Far from being passive residents, supermassive black holes actively shape their galactic homes, influencing star formation, controlling the movement of cosmic gas, and even determining the ultimate fate of entire star systems. They are, in many ways, the architects of the cosmic landscapes we observe. Think for a moment about the scale we're discussing. Our Sun, a fairly average star, has a mass of about 2 × 10⁻30 kilograms, a number so large it's difficult to comprehend. Now imagine an object with a mass billions of times greater, all compressed into a region that could fit within the orbit of Neptune. The density and gravitational power of such an object defy our everyday understanding of how matter behaves. At the event horizon of a supermassive black hole, space and time themselves are warped beyond recognition. Yet despite their extreme nature, supermassive black holes are surprisingly common in our universe. Astronomers now believe that virtually every large galaxy harbors one of these giants at its center. Our own Milky Way galaxy is home to a supermassive black hole called Sagittarius A star, with a mass of about 4 million times that of our Sun. While this might sound enormous, and indeed, by human standards, it is, Sagittarius A star is actually relatively modest compared to some of the true giants we've discovered elsewhere in the cosmos. The largest supermassive black holes discovered so far have masses tens of billions of times greater than our Sun. The current record holder is believed to be the black hole at the center of the galaxy TON 618, with an estimated mass of 66 billion solar masses. To put this in perspective, if our Sun were the size of a grain of sand, this black hole would be the size of a building several stories tall. Such extreme objects raise profound questions about how nature can create entities of such immense mass and density. For decades, these cosmic titans remained theoretical, mathematical curiosities born from Einstein's equations, but seemingly too extreme to exist in reality. Scientists wondered, could objects of such immense density and gravitational power actually exist? The answer, we now know with certainty, is yes. Not only do they exist, but they're surprisingly common, lurking at the center of virtually every large galaxy we can observe. The discovery and confirmation of supermassive black holes has been one of astronomy's greatest triumphs, a testament to human ingenuity and our relentless pursuit of understanding the universe's deepest mysteries. It required revolutionary technologies, creative thinking, and international cooperation on a scale rarely seen in science. From the development of radio astronomy in the mid-20th century to the recent achievement of directly imaging a black hole silhouette with the Event Horizon Telescope, each technological advance has brought new insights into these cosmic beasts. The first hints that something extraordinary lurked at the centers of galaxies came in the 1960s, when astronomers discovered quasars, incredibly bright, distant objects that outshone entire galaxies despite appearing to be no larger than a star. The energy output of these mysterious objects was staggering, equivalent to hundreds of normal galaxies combined. What could possibly generate such enormous amounts of energy from such a compact region? The answer we now know is a supermassive black hole in the process of feeding. As material falls toward a black hole, it forms a spinning disk of gas and dust called an accretion disk. The incredible gravitational forces and friction within this disk heat the material to millions of degrees, causing it to glow brightly across the electromagnetic spectrum. In the most extreme cases, those we call quasars, this process releases energy that can be detected across billions of light years of space. But not all supermassive black holes are active feeders. Many, including the one at the center of our own galaxy, are relatively quiet. At least for now, they consume material at a much lower rate, occasionally swallowing a passing cloud of gas or perhaps an unwary star that strays too close. Yet even these more dormant black holes exert a powerful influence on their surroundings, their immense gravity helping to shape the motion of stars and gas throughout their host galaxies. When we first confirmed the existence of supermassive black holes, it fundamentally changed our understanding of cosmic evolution. We realized that galaxies and their central black holes grow together, influencing each other in a cosmic dance that spans billions of years. These black holes aren't just passive features of galaxies, they're active participants in galactic evolution, sometimes nurturing star formation and sometimes quenching it entirely. This relationship between galaxies and their central black holes is one of the most fascinating aspects of modern astronomy. Observations have revealed a surprising correlation between the mass of a supermassive black hole and the properties of its host galaxy, particularly the mass and velocity dispersion of the galaxy's central bulge of stars. This relationship, often called the M-sigma relation, suggests a deep connection between black hole growth and galaxy formation that astronomers are still working to understand. How could a black hole, despite its enormous mass, influence the evolution of an entire galaxy containing hundreds of billions of stars spread across tens of thousands of light years? The answer lies in the extraordinary amounts of energy that can be released when black holes actively feed. As material falls into a supermassive black hole, some of the energy is converted into radiation and particle jets that can heat and push away surrounding gas, effectively regulating the fuel supply for new star formation throughout the galaxy. This process, known as black hole feedback, represents one of the most important ways that supermassive black holes shape cosmic evolution. By controlling the rate at which stars form within galaxies, these black holes help determine the overall properties and appearance of the galaxies we observe today. Without understanding supermassive black holes, we cannot fully understand how galaxies form and evolve over cosmic time. Perhaps most astonishing is how these giants form in the first place. How does nature create objects of such extreme density and mass? The process remains one of astronomy's most intriguing puzzles, with several competing theories but no definitive answer. Did they form from the direct collapse of enormous clouds of gas in the early universe? Did they grow gradually from smaller black holes that merged together? Or is there some other process at work that we haven't yet discovered? The evidence suggests that supermassive black holes were already present in the very early universe, just a few 100 million years after the Big Bang. Astronomers have observed quasars powered by billion solar mass black holes when the universe was less than a billion years old. This creates a timing problem. How could such enormous objects form so quickly? The mystery of their origin remains one of the most active areas of research in modern astrophysics. One possibility is that the first black holes formed from the collapse of the earliest stars. Massive, short-lived giants composed almost entirely of hydrogen and helium. When these first-generation stars exhausted their nuclear fuel, they would have collapsed to form black holes with masses perhaps 100 times that of our Sun. These seed black holes could then have grown by accreting gas and merging with other black holes, eventually reaching supermassive status. Another theory suggests a more direct route to forming supermassive black holes. In the early universe, enormous clouds of gas might have collapsed directly into black holes, bypassing the star formation stage entirely. This direct collapse scenario could explain how billion solar mass black holes appeared so soon after the Big Bang, but it requires very specific conditions that astronomers are still working to understand. The journey to understanding supermassive black holes has been filled with surprising discoveries. We've found that some are relatively quiet, like the one at the center of our own Milky Way, which is relatively dormant, occasionally snacking on passing clouds of gas. Others are extraordinarily active, devouring material at astounding rates and blasting out energy that can be seen across billions of light years. These are the objects we call quasars and active galactic nuclei. In recent years, our ability to study these cosmic beasts has improved dramatically. In 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole shadow, the supermassive black hole at the center of the galaxy Messier 87. This remarkable achievement, involving 8 radio telescopes around the world working together as a single Earth-sized observatory, gave us our first visual confirmation of the theory of black holes that Einstein's equations had predicted a century earlier. Another revolutionary advance came with the detection of gravitational waves, ripples in the fabric of spacetime caused by the collision and merger of black holes. While the current generation of gravitational wave detectors like LIGO and Virgo are primarily sensitive to mergers of stellar mass black holes, future space-based detectors like LISA will be able to detect the mergers of supermassive black holes, opening an entirely new window on these cosmic giants. In this journey through cosmic extremes, we'll explore the nature, formation, and impact of these cosmic monsters. We'll visit the largest black holes ever discovered, such as the behemoth at the center of the galaxy TON 618, which contains enough mass to make 40 billion suns. We'll witness the violent aftermath when 2 supermassive black holes collide following a galactic merger, and we'll venture to the very edge of the event horizon to understand what happens at this point of no return. We'll explore how supermassive black holes launch enormous jets of particles traveling at nearly the speed of light, creating structures that can span millions of light years, larger than entire galaxies. We'll investigate the connection between black holes and dark matter, the mysterious substance that makes up most of the mass in our universe. And we'll consider what the study of these extreme objects tells us about the fundamental laws of physics. The story of supermassive black holes is, in many ways, the story of our universe itself, a tale of extreme conditions, colossal forces, and the delicate balance between creation and destruction. These cosmic beasts represent nature at its most extreme, showing us what happens when ordinary physics is pushed to extraordinary limits. They challenge our understanding of gravity, space, time, and matter, forcing us to confront the boundaries of our knowledge. As we peer into the darkness at the centers of galaxies, we're really looking into the engines that power cosmic evolution itself. We're witnessing the most powerful forces in nature at work, sculpting the universe into the form we see today. Through understanding these giants, we come to better understand our own place in the cosmic story. For even our own galaxy is shaped by the supermassive black hole that lurks at its heart, some 26,000 light-years from Earth. The study of supermassive black holes also opens profound philosophical questions about the nature of reality. At the event horizon, the boundary beyond which nothing can escape, our current understanding of physics begins to break down. What happens to matter and information that falls into a black hole? Does it truly disappear from our universe, or is it preserved in some form? These questions touch on the fundamental nature of space, time, and information itself. Some theoretical physicists, including Stephen Hawking, have proposed that black holes slowly evaporate over time through a process now known as Hawking radiation. If true, this would mean that black holes aren't truly black. They emit a faint glow of particles created through quantum effects near their event horizons. For stellar mass black holes, this evaporation would take longer than the current age of the universe. But for the truly massive black holes at galactic centers, the process would take unimaginably longer, on the order of 10 to the power of 100 years, a time span so vast it dwarfs the current age of the universe by a factor of billions upon billions. To truly grasp what makes these cosmic beasts so extraordinary, we must first understand what sets them apart from their smaller cousins, the stellar black holes that form when massive stars die. While sharing some fundamental properties, supermassive black holes represent an entirely different class of object, with origins and impacts that are unique in the cosmos. In the next part of our journey, we'll explore these differences in detail, uncovering what makes the supermassive variety particularly special. So join us as we embark on this journey into cosmic extremes, venturing to the very edge of what we know about the universe and peering into the darkness beyond. The mysteries of supermassive black holes await, and what we discover there will forever change how we view the cosmos and our place within it. From their mysterious origins in the early universe to their ultimate fate in the distant future, these cosmic beasts have much to teach us about the nature of reality itself. To truly comprehend the nature of supermassive black holes, we must first understand what sets them apart from their cosmic cousins. Black holes come in different varieties, each with distinct origins and characteristics, yet all sharing the fundamental property that defines a black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape once it passes the event horizon. The smallest variety, known as stellar black holes, form when massive stars reach the end of their lives. When a star at least 20 times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against the inward pull of gravity. The star's core collapses, triggering a spectacular supernova explosion, while the central region implodes to form a black hole. These stellar remnants typically have masses between 5 and 100 times that of our Sun, compressed into a region smaller than a city on Earth. Imagine a sphere with the mass of 10 suns, yet smaller than Manhattan. That's the extraordinary density of a stellar black hole. While impressive, these objects pale in comparison to their supermassive counterparts. The difference between a stellar black hole and a supermassive black hole is like comparing a grain of sand to Mount Everest. They operate on entirely different scales. In the middle range, we find what astronomers call intermediate mass black holes, with masses between 100 and 100,000 times that of our Sun. These mysterious objects have proven elusive, with only a handful of confirmed candidates discovered so far. They might form through the merger of smaller black holes or through special conditions in dense star clusters. Some scientists believe these intermediate black holes could serve as the building blocks or seeds that eventually grow into supermassive black holes, though this remains an active area of research. And then we come to the true giants, supermassive black holes. These cosmic behemoths have masses ranging from millions to billions of times that of our Sun. The supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A star, weighs in at about 4 million solar masses. While this might sound enormous, it's actually quite modest compared to the true monsters lurking in other galaxies. The largest confirmed supermassive black hole discovered so far resides in the galaxy TON 618, with an estimated mass of 66 billion solar masses, more than 15,000 times more massive than our own galactic center. To put this in perspective, if our Sun were the size of a basketball, This black hole would be as large as the Earth's orbit around the Sun. The scale is truly mind-boggling. Yet despite their enormous mass, supermassive black holes can be surprisingly compact. The event horizon of Sagittarius A star, the point of no return, has a radius of only about 12 million kilometers. That's just 17 times the radius of our Sun, or about 1/12 the distance from the Earth to the Sun. For something containing the mass of 4 million suns, this is extraordinarily dense. This brings us to a fundamental property of black holes. Their size scales directly with their mass. The radius of a black hole's event horizon, known as the Schwarzschild radius, is proportional to its mass. Double the mass, and you double the radius. This means that while supermassive black holes contain billions of times more mass than stellar black holes, they are not billions of times larger in physical size. Their event horizons are merely millions or billions of kilometers across, rather than just dozens or hundreds. What truly sets supermassive black holes apart, beyond their enormous mass, is where we find them. Unlike stellar black holes, which can form anywhere a massive star reaches the end of its life, supermassive black holes are almost exclusively found at the centers of galaxies. Nearly every large galaxy we've studied appears to harbor one of these giants at its core, suggesting a deep connection between galaxy formation and the growth of supermassive black holes. This central location gives supermassive black holes tremendous influence over their host galaxies. Sitting at the gravitational focal point, they help determine the orbits of stars in the galactic bulge, influence the flow of gas throughout the galaxy, and can even affect star formation rates across tens of thousands of light years. When active, they can launch jets of particles and radiation that extend far beyond the galaxy itself, interacting with the intergalactic medium and potentially influencing neighboring galaxies. The environments around supermassive black holes are some of the most extreme in the universe. Close to the event horizon, orbital velocities approach the speed of light, and the intense gravitational field creates effects predicted by Einstein's theory of general relativity. Time itself flows more slowly in this deep gravitational well, a phenomenon known as gravitational time dilation. An observer watching from a safe distance would see objects near the black hole appearing to move in slow motion as they approach the event horizon. Another key difference between supermassive black holes and their smaller relatives lies in the density of matter. While this might seem counterintuitive, supermassive black holes actually have lower average densities than stellar black holes. This is because density is mass divided by volume, and volume increases with the cube of radius. Since a supermassive black hole's radius is proportional to its mass, its volume increases more rapidly than its mass as it grows larger. The result is that while a stellar black hole might have a density trillions of times greater than water, the average density of a supermassive black hole can be comparable to water or even air. Of course, this is the average density within the event horizon. The actual density distribution within a black hole remains one of physics' greatest mysteries, hidden behind the veil of the event horizon. What happens beyond the event horizon? This is where our current understanding of physics begins to break down. According to general relativity, at the center of a black hole lies a singularity, a point of infinite density, where space-time itself becomes infinitely curved. Many physicists believe that this mathematical singularity indicates a failure of our current theories rather than a physical reality. A complete theory of quantum gravity, which would unite quantum mechanics with general relativity, might resolve this paradox. But such a theory remains one of science's great unfinished projects. The influence of a supermassive black hole extends far beyond its event horizon. Surrounding this boundary is a region called the ergosphere, where space-time itself is dragged along by the black hole's rotation in a process called frame dragging. Within the ergosphere, it becomes impossible for matter to remain stationary relative to distant space. Everything must rotate with the black hole, though it's still possible to escape from this region unlike the event horizon. Further out, we find the accretion disk, a flattened band of gas and dust spiraling toward the black hole. As material in this disk falls inward, it heats up due to friction and compression, reaching temperatures of millions of degrees. This superheated plasma emits radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. For actively feeding supermassive black holes, these accretion disks can outshine entire galaxies, producing the phenomena we call quasars and active galactic nuclei. Some supermassive black holes also produce enormous jets of particles traveling at nearly the speed of light. These relativistic jets can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of the host galaxy. Formed through complex interactions between the black hole's magnetic field and the accretion disk, these jets represent some of the most energetic processes in the universe, capable of influencing the evolution of entire galaxy clusters. The way supermassive black holes bend space-time around them creates other fascinating effects. One is gravitational lensing, where light from distant objects is bent as it passes near the black hole. This can create multiple images of the same background object, distort the appearance of stars and galaxies, or even form complete rings of light called Einstein rings. Astronomers use these gravitational lensing effects to study both the black holes themselves and the distant objects whose light is being lensed. Another remarkable feature of supermassive black holes is their potential longevity. While stellar black holes slowly evaporate through a quantum process called Hawking radiation, the time frame for this evaporation scales with the cube of the black hole's mass. A stellar black hole might evaporate over an unimaginably long period of about 10 to the power of 67 years, but a supermassive black hole would take vastly longer, on the order of 10 to the power of 100 years or more. For comparison, the current age of the universe is about 14 billion years, or 1.4 times 10 to the power of 10 years, a mere instant compared to a supermassive black hole's lifetime. This extraordinary longevity means that once formed, supermassive black holes are essentially permanent features of our universe, at least on any timescale relevant to cosmic evolution as we currently understand it. They will outlast stars, planets, and possibly even the protons that make up ordinary matter, assuming current theories about proton decay are correct. In the far, far future, when the universe has grown dark and cold, supermassive black holes may be among the last organized structures remaining. How do we measure the mass of these cosmic giants? Unlike planets or stars, we can't directly weigh a black hole. Instead, astronomers use several indirect methods to estimate their masses. For supermassive black holes in nearby galaxies, the most reliable method involves tracking the orbits of stars or gas clouds around the galactic center. By measuring their velocities and orbital periods, astronomers can apply Kepler's laws of orbital motion to calculate the central mass required to maintain those orbits. This method has been used with remarkable precision for Sagittarius A star, the supermassive black hole at the center of our own galaxy. By tracking individual stars over decades using adaptive optics on large ground-based telescopes, astronomers have determined its mass to be about 4.3 million solar masses, with an uncertainty of just a few %. These observations earned the two leading researchers, Andrea Ghez and Reinhard Genzel, a share of the 2020 Nobel Prize in Physics. For more distant galaxies where individual stars can't be resolved, astronomers use other techniques. One approach measures the velocity dispersion of stars in the galaxy's central bulge, then applies the m-sigma relation, an empirical correlation between black hole mass and stellar velocity dispersion. Another method, called reverberation mapping, measures the time delay between fluctuations in the light from the accretion disk and corresponding changes in gas clouds orbiting farther out. This time delay, combined with the speed of light, allows astronomers to determine the size of the region and thus estimate the black hole's mass. The rotation of supermassive black holes represents another crucial aspect of their physics. Unlike stellar black holes, which inherit their spin from the rotation of their parent stars, Supermassive black holes can acquire angular momentum through a variety of processes over their long lifetimes. These include the directionality of infalling matter, alignment with the rotation of their host galaxies, and mergers with other black holes. A rapidly spinning supermassive black hole can have profound effects on its surroundings. The frame-dragging effect becomes more pronounced, the ergosphere extends farther from the event horizon, and the efficiency of energy extraction from infalling matter increases dramatically. Some theories suggest that the powerful jets observed from active galactic nuclei are powered by energy extracted from the black hole's rotation through a process called the Blandford-Znayak mechanism, effectively tapping into the enormous rotational energy stored in the black hole itself. The extreme conditions near supermassive black holes make them natural laboratories for testing the limits of physics. The intense gravitational fields provide opportunities to test Einstein's theory of general relativity under conditions impossible to recreate on Earth. Observations of stars orbiting Sagittarius A star, gas dynamics in active galactic nuclei, and the shadow of the event horizon imaged by the Event Horizon Telescope have all provided strong confirmation of general relativity's predictions. Yet these same extreme conditions also point to the limits of our current understanding. At the event horizon and beyond, the classical theory of general relativity predicts behavior that conflicts with quantum mechanics, creating paradoxes that have puzzled physicists for decades. The resolution of these paradoxes likely requires a quantum theory of gravity, a theoretical framework that would unite Einstein's description of gravity with the principles of quantum mechanics. Some of the most promising attempts to develop such a theory come from string theory and loop quantum gravity. These approaches suggest that at the smallest scales, spacetime itself might have a discrete quantum structure, rather than being the smooth continuum described by general relativity. If true, this would mean that the singularities predicted at the centers of black holes might be replaced by more complex structures that avoid the mathematical infinities that plague our current theories. The concept of the event horizon itself has been challenged by some theoretical physicists. Stephen Hawking proposed that quantum effects near the event horizon could lead to information leakage from the black hole, contradicting the classical view that nothing can escape. This led to the famous black hole information paradox, which remains unresolved. More recently, some theorists have suggested that the event horizon might be replaced by a firewall of high-energy particles, or could even be a kind of holographic illusion, with the true nature of black holes being quite different from our classical understanding. Despite these theoretical uncertainties, the observational evidence for supermassive black holes is overwhelming. From the motions of stars at the centers of nearby galaxies to the enormous energy output of distant quasars, from the jets extending from active galactic nuclei to the direct imaging of black hole shadows, multiple independent lines of evidence confirm that these cosmic monsters are real physical entities, not merely theoretical constructs. As our understanding of supermassive black holes continues to evolve, one question looms larger than others. How did these giants form in the first place? The origin of supermassive black holes remains one of the most intriguing puzzles in modern astrophysics, with significant implications for our understanding of galaxy formation, cosmic evolution, and the fundamental laws of physics. In our next chapter, we'll explore the leading theories and the observational evidence that constrains them as we seek to understand the birth of these cosmic titans. Perhaps the greatest mystery surrounding supermassive black holes is their origin. How does nature create objects of such extraordinary mass and density? This question becomes even more perplexing when we consider that many of these cosmic giants appear to have been fully formed when the universe was still in its infancy. Observations have revealed quasars, extremely bright objects powered by actively feeding supermassive black holes, that existed less than 1 billion years after the Big Bang, when the universe was less than 7% of its current age. One such example is the quasar J0130+3130, discovered in 2011, which harbors a black hole with a mass of 12 billion suns that formed when the universe was only 870 million years old. More recently, astronomers have pushed these observations even further back in time, finding black holes with masses of billions of solar masses when the universe was only a few hundred million years old. Barely enough time for the first stars to form, live out their lives and die, let alone for such enormous black holes to grow through conventional means. This timing problem represents one of the most significant challenges to our understanding of supermassive black hole formation. The conventional process of black hole growth through accretion, the gradual accumulation of matter, seems too slow to explain how billion solar mass black holes could form so early in cosmic history. While matter falling into a black hole can do so at tremendous rates, there is a theoretical limit to this process, known as the Eddington limit, beyond which the pressure of the radiation emitted by the superheated infalling material pushes away additional material that would otherwise be captured. At this Eddington limited rate of growth, it would take a stellar mass black hole, say one with 100 times the mass of our Sun, more than 1 billion years to grow to 1 billion solar masses. Yet we observe black holes that have accomplished this feat in much less time. Something doesn't add up. Either these early black holes started from much larger seeds, they grew at rates exceeding the theoretical limits, or they formed through some entirely different mechanism. Let's explore the leading theories for how these cosmic giants came to be, starting with what astronomers call the light seed scenario. In this model, supermassive black holes begin as relatively small black holes formed from the death of the universe's first generation of stars. These population 3 stars, as astronomers call them, were unlike any stars we see today. Formed from pristine gas containing only hydrogen and helium, the elements created in the Big Bang, these stars lack the heavier elements that help modern stars regulate their energy output. Without these heavier elements, population 3 stars could grow to extraordinary sizes, perhaps hundreds or even 1,000 times more massive than our Sun. When these behemoths exhausted their nuclear fuel, after just a few million years of life, they would collapse directly into black holes with masses of perhaps 100 to 500 solar masses. These would be the seeds that, through accretion and mergers over billions of years, would eventually grow into the supermassive black holes we observe today. The light seed scenario has the advantage of following naturally from our understanding of stellar evolution. We know that massive stars can form black holes when they die, and we have observed stellar mass black holes throughout our galaxy. The challenge lies in explaining how these relatively small seeds could grow quickly enough to reach billions of solar masses within the first billion years of cosmic history. Standard accretion physics suggests they simply couldn't grow fast enough, even if they were feeding continuously at the maximum theoretical rate. One possible solution involves periods of super Eddington accretion, growth rates that exceed the theoretical limit. Under certain conditions, such as in a dense, chaotic environment with irregular gas flow patterns, a black hole might be able to consume matter faster than the Eddington limit would suggest. The radiation pressure that would normally push away infalling material might escape through low-density channels, allowing the high-density regions to continue falling inward unimpeded. Some theoretical models and computer simulations suggest this might be possible, though the details remain uncertain. Another possibility is that early black holes grew not just by consuming gas, but also by merging with other black holes. When galaxies collide, which happened frequently in the early dense universe, their central black holes can eventually find each other and merge, combining their masses. A series of such mergers could accelerate the growth process, helping to explain how billion solar mass black holes could form within the first billion years after the Big Bang. An alternative to the light seed scenario is what astronomers call the heavy seed or direct collapse model. Instead of starting from the remnants of dead stars, this theory suggests that some supermassive black holes formed directly from the collapse of enormous clouds of gas in the early universe. Bypassing the star formation stage entirely, under the right conditions, a massive cloud of primordial gas might collapse directly into a black hole with an initial mass of thousands or even hundreds of thousands of solar masses, providing a significant head start on the growth process. For this direct collapse to occur, the gas cloud would need to avoid fragmenting into smaller clumps that would form stars. Normally, as a gas cloud collapses under its own gravity, it breaks apart into smaller and smaller pieces, eventually forming a cluster of stars rather than a single massive object. To prevent this fragmentation, the gas would need to remain hot, which suppresses the formation of smaller structures. One way to keep the gas hot would be the absence of cooling agents like metals and molecular hydrogen. In the early universe, before the first generation of stars had enriched the interstellar medium with heavier elements, gas clouds consisted primarily of atomic hydrogen and helium. If molecular hydrogen could be prevented from forming, perhaps by a strong ultraviolet radiation field from nearby stars, the cloud would lack efficient cooling mechanisms, remaining hot as it collapsed. Another factor that might facilitate direct collapse is the presence of strong turbulence or a tidal field from a nearby galaxy, which could disrupt the normal star formation process. The collapse would also need to occur in a region with exceptionally high gas density, such as at the intersection of several cosmic filaments in the early web-like structure of the universe. If all these conditions align, theoretical models suggest that a gas cloud could collapse directly to form a black hole with an initial mass of perhaps 10,000 to 100,000 solar masses. These heavy seeds would then have a significant advantage in reaching billion solar mass status within the first billion years of cosmic history, requiring much less extreme growth rates than the light seed scenario. The direct collapse theory has gained support in recent years, as it elegantly solves the timing problem of early supermassive black holes. However, it faces its own challenges. The conditions required for direct collapse may have been rare in the early universe, which doesn't explain the apparently ubiquitous nature of supermassive black holes in present-day galaxies. Additionally, the process has yet to be observed directly, though astronomers are actively searching for objects that might represent the aftermath of such an event. A third possibility combines elements of both previous scenarios. Perhaps some supermassive black holes formed from stellar remnants, while others formed through direct collapse. The mechanism might have varied depending on local conditions, with direct collapse occurring in regions with particularly high gas density and strong radiation fields, and the stellar remnant pathway dominating elsewhere. Over time, these different populations may have evolved similarly, explaining the relatively uniform properties of supermassive black holes we observe today. Recent observations have provided tantalizing clues about the formation process. The discovery of intermediate mass black holes, objects with masses between 100 and 100,000 solar masses, suggests that there may indeed be a continuous spectrum of black hole masses, rather than two distinct populations. These intermediate objects could represent either growing light seeds on their way to becoming supermassive, or the result of direct collapse events that produce black holes smaller than theoretically predicted. One such intermediate mass black hole candidate was discovered in 2020 in a stellar cluster called NGC 6404, with an estimated mass of around 20,000 solar masses. Objects like this might represent the missing link between stellar black holes and their supermassive cousins, providing valuable insights into the growth process. The James Webb Space Telescope, launched in December 2021, is expected to revolutionize our understanding of black hole formation by observing the earliest quasars in unprecedented detail and potentially discovering even earlier examples than currently known. By analyzing the properties of these ancient objects and their host galaxies, astronomers hope to constrain the possible formation mechanisms and determine which scenario, light seeds, heavy seeds, or some combination, best explains the origin of supermassive black holes. Another line of evidence comes from studying the relationship between supermassive black holes and their host galaxies in the present-day universe. The tight correlation between black hole mass and galaxy properties suggests a coevolution process where the growth of the black hole and the development of the galaxy influence each other. This relationship might contain clues about the initial formation mechanism and subsequent growth history of supermassive black holes. Computer simulations of cosmic evolution have also provided valuable insights. These simulations attempt to recreate the formation and growth of structure in the universe, from the nearly uniform distribution of matter shortly after the Big Bang to the complex web of galaxies, clusters, and voids we observe today. By including different models of black hole formation and growth, researchers can test which scenarios produce results that match observations. Some of the most sophisticated simulations, such as the illustrious TNG project, suggest that a combination of mechanisms might be at work. These simulations show that both accretion and mergers play important roles in black hole growth, with their relative importance varying depending on the environment and cosmic epoch. During periods of intense star formation, known as cosmic noon, about 10 billion years ago, accretion dominated the growth process. In contrast, during quieter periods, mergers between black holes following galaxy collisions became more significant. The merger of black holes represents a particularly important aspect of their growth history. When galaxies collide, which happens frequently in cosmic history, their central black holes don't immediately merge. Instead, they begin a complex dance that can last millions or even billions of years. First, the black holes sink toward the center of the newly merged galaxy through a process called dynamical friction, where they lose energy through gravitational interactions with surrounding stars. Once they come within a few light years of each other, the black holes form a binary system, orbiting around their common center of mass. The separation continues to shrink as the binary system interacts with nearby stars. But this process becomes increasingly inefficient at smaller separations, potentially leading to a situation where the black holes stall at a separation of about 1 light-year, a problem known as the final parsec problem. For the black holes to merge completely, they need to overcome this barrier, which likely happens through interaction with gas in the galactic center or by the presence of a third black hole that disrupts the stable binary orbit. When the black holes finally come, within a few times their Schwarzschild radii of each other, they enter the regime where gravitational waves, ripples in spacetime, predicted by Einstein's theory of general relativity, become the dominant mechanism for energy loss, rapidly bringing the black holes together in a final violent merger. These mergers not only contribute to the growth of supermassive black holes, but also produce some of the most energetic events in the universe. A typical merger between two supermassive black holes releases energy equivalent to converting several solar masses entirely into radiation, primarily in the form of gravitational waves. While these waves are too low in frequency to be detected by current observatories like LIGO and Virgo, future space-based detectors like LISA, Laser Interferometer Space Antenna, will be sensitive to these events, potentially observing multiple supermassive black hole mergers per year throughout the observable universe. Such observations will provide a wealth of information about the distribution, masses, and spins of supermassive black holes, offering new insights into their formation history. The detailed waveforms of these gravitational wave signals will carry information about the black hole's properties before, during, and after the merger, allowing astronomers to trace their evolution over cosmic time. The growth of supermassive black holes isn't a continuous process, but rather occurs in distinct episodes. For much of their lives, these black holes are relatively dormant, accreting matter at low rates and having minimal impact on their surroundings. However, certain events can trigger periods of intense activity when the black hole consumes matter at rates approaching the theoretical maximum. One such trigger is a galaxy merger, which can funnel large amounts of gas toward the galactic center, feeding the black hole and potentially triggering a quasar phase. Another is a close encounter with a massive cloud of gas or a star, which can be disrupted by the black hole's tidal forces and form a temporary accretion disk. In rare cases, a star may pass so close to the black hole that it is completely torn apart in what astronomers call a tidal disruption event, providing a brief but substantial meal for the cosmic beast. These episodic feeding events help explain the observed properties of supermassive black holes and their host galaxies. The energy released during active phases can heat or expel gas from the galactic center, temporarily halting both star formation and further black hole growth, a self-limiting process that helps establish the observed correlation between black hole mass and galaxy properties. The future of supermassive black hole growth varies depending on their environment. In the centers of massive galaxy clusters, the largest black holes may continue to grow through occasional mergers and the accretion of hot gas. In contrast, black holes in isolated galaxies may have largely completed their growth, remaining dormant for the foreseeable cosmic future as their fuel supply dwindles. In our own Milky Way, the supermassive black hole Sagittarius A star is currently in a dormant phase, accreting material at just a tiny fraction of the Eddington limit. However, in about 4 billion years, our galaxy will collide with the neighboring Andromeda galaxy, likely triggering a new phase of activity as the two galaxies' central black holes eventually merge. This event will create a black hole with a combined mass of about 100 million solar masses at the heart of the newly formed galaxy, sometimes called Milkomeda by astronomers. Looking back at the early universe, the existence of fully formed supermassive black holes within the first billion years after the Big Bang remains one of astronomy's most fascinating puzzles. The seeds of these cosmic monsters must have been planted during cosmic dawn, the period when the first stars and galaxies were just beginning to form. Understanding this process requires pushing our observations to the very edge of the observable universe, looking back in time to witness the birth of these extraordinary objects. As we continue to explore the cosmos with increasingly powerful telescopes and innovative observational techniques, we move closer to answering the fundamental question of how supermassive black holes form. Each new discovery, whether it's an even earlier quasar, an intermediate mass black hole, or a gravitational wave signal from a distant merger, adds another piece to the puzzle, helping us reconstruct the life story of these cosmic giants from birth to maturity. The formation of supermassive black holes represents one of the most extreme processes in our universe, operating at the boundaries of our current understanding of physics. By unraveling this mystery, we gain insights not only into these extraordinary objects, but also into the fundamental laws that govern space, time, and gravity, the very fabric of reality itself. And while we may not yet have all the answers, the journey of discovery continues, driven by humanity's unquenchable curiosity about the cosmic engines that have helped shape our universe from its earliest moments to the present day. Far from being mere passive residents, supermassive black holes play a crucial and active role in shaping the galaxies they inhabit. For decades, astronomers viewed these cosmic behemoths as interesting but perhaps incidental features of galactic centers, exotic objects that had little impact on the broader evolution of their host galaxies. This view has been completely overturned by observations over the past 25 years, revealing that supermassive black holes are, in fact, key architects of cosmic structure, influencing everything from the rate of star formation to the very size and shape of their galactic homes. The first hint of this profound connection came in the 1990s, when astronomers discovered a surprising correlation between the mass of a galaxy's central supermassive black hole and the velocity dispersion of stars in the galaxy's bulge, a relationship now known as the M-sigma relation. This tight correlation suggests that the growth of the black hole and the development of the galaxy are intimately linked, despite the enormous difference in scale between the two. A typical supermassive black hole has a gravitational influence that extends only a few light years from the galactic center, yet somehow it knows about and correlates with properties of the galaxy that extend tens of thousands of light years beyond its direct gravitational reach. The M-sigma relation is remarkably precise. The mass of the central black hole is proportional to approximately the fourth power of the velocity dispersion of the stars in the galactic bulge. This means that if one galaxy has stars moving twice as fast as another galaxy, on average, its central black hole will be about 16 times more massive. The relationship holds across galaxies spanning a wide range of masses and types, from relatively small elliptical galaxies to massive spiral systems like our own Milky Way. Further research revealed additional correlations. The mass of the central black hole also correlates strongly with the mass of the galaxy's central bulge of stars, typically amounting to about 0.1% of the bulge mass. This precise ratio appears across galaxies of vastly different sizes and ages, suggesting a fundamental regulatory mechanism that maintains this proportion throughout cosmic history. These correlations raised a profound question. How does a relatively small object, like a supermassive black hole, influence galaxy-wide properties? The answer lies in the extraordinary amounts of energy that can be released when black holes actively feed on surrounding matter, a process called accretion. During periods of intense activity, a feeding supermassive black hole can release energy equivalent to the conversion of several solar masses into pure energy each year, making it the most energetic single phenomenon in the universe. This energy is released in various forms, including electromagnetic radiation, spanning the spectrum from radio waves to gamma rays, as well as kinetic energy in the form of powerful jets and winds. These outputs can heat the surrounding gas, drive outflows that expel material from the galaxy, and even affect the intergalactic medium beyond the galaxy's boundaries. The process through which the energy from the black hole affects its surroundings is known as feedback, and it represents one of the most important mechanisms regulating galaxy evolution. Black hole feedback operates in multiple modes. During periods of intense accretion, such as those observed in quasars and active galactic nuclei, the radiation pressure from the superheated accretion disk can push away surrounding gas, effectively shutting off the fuel supply for both the black hole and for star formation throughout the galaxy's central regions. This quasar mode feedback is particularly important in massive galaxies, where it can expel or heat large amounts of gas, preventing it from cooling and forming new stars. Another form of feedback involves the jets of particles emitted from the regions near the black hole. These relativistic jets, traveling at speeds approaching that of light, can extend far beyond the boundaries of the galaxy itself, interacting with the hot gas that surrounds the galaxy in what astronomers call the circumgalactic medium. As these jets push through this medium, they create enormous bubbles or cavities, visible in X-ray observations of galaxy clusters. This radio mode feedback is particularly important in maintaining the temperature of gas in and around massive galaxies, preventing it from cooling and flowing inward to form new stars or feed the black hole. The impact of black hole feedback varies depending on the mass and environment of the galaxy. In massive elliptical galaxies at the centers of galaxy clusters, radio mode feedback plays a crucial role in preventing the hot gas that permeates the cluster from cooling and flowing toward the central galaxy, a process that would otherwise result in excessive star formation and black hole growth. This feedback creates a self-regulating system. If the gas begins to cool and flow inward, it feeds the black hole, which then becomes more active and heats the gas, preventing further cooling and inflow. In less massive galaxies, including spirals like our Milky Way, the role of the central black hole may be less dominant but still significant. During periods of activity, the radiation and outflows from the black hole can influence the temperature and motion of gas in the galactic center, affecting star formation rates and the overall evolution of the galaxy's structure. In our own galaxy, there's evidence that the currently dormant Sagittarius A star has experienced periods of higher activity in the past, potentially influencing the evolution of the inner regions of the Milky Way. The relationship between supermassive black holes and their host galaxies extends beyond these feedback mechanisms. The presence of a massive central object can fundamentally alter the orbital dynamics of stars in the galactic bulge, influencing the shape and density profile of the central regions. In some cases, the gravitational influence of the black hole can create distinct structures, such as nuclear star clusters or stellar disks, in the innermost parts of the galaxy. The role of supermassive black holes becomes particularly dramatic during galaxy mergers. When two galaxies collide and begin to merge, their central black holes eventually find each other and form a binary system before ultimately coalescing. This process can take hundreds of millions or even billions of years, during which the binary black hole system can fling surrounding stars onto new orbits through gravitational interactions, potentially altering the structure of the merging galaxy's center. The final merger of the two black holes releases an enormous amount of energy in the form of gravitational waves, ripples in the fabric of spacetime that travel outward at the speed of light. While these waves themselves carry away energy and angular momentum from the black hole system, they have minimal direct impact on the surrounding galaxy due to their weak interaction with matter. However, if the merging black holes have unequal masses or spins, the merged black hole can receive a recoil kick due to the asymmetric emission of gravitational waves, potentially causing it to oscillate within or even be ejected from the galaxy center, further influencing the galaxy's structure. Beyond these dynamic influences, supermassive black holes play a crucial role in determining the overall appearance and properties of their host galaxies. The tight correlation between black hole mass and bulge properties suggests that the growth of both structures is coordinated, with neither able to significantly outpace the other. This coordination helps explain why galaxies fall into distinct types, with clear relationships between their mass, shape, star formation rate, and central black hole properties. In spiral galaxies like our Milky Way, the central black hole coexists with a dense concentration of stars known as the bulge, which appears as a roughly spherical region at the center of the disk. The size and mass of this bulge correlate with the mass of the central black hole, suggesting a co-evolution process throughout the galaxy's history. Galaxies with more massive central black holes tend to have more prominent bulges, while those with smaller black holes often have smaller, less massive central concentrations of stars. Elliptical galaxies, which lack the disk structure of spirals and consist primarily of older stars in a roughly ellipsoidal distribution, also show a strong relationship between their central black hole and their overall properties. The most massive elliptical galaxies, often found at the centers of galaxy clusters, harbor the largest known supermassive black holes, with masses up to tens of billions of solar masses. These enormous black holes likely grew through multiple mergers as their host galaxies consumed smaller neighbors over cosmic time. The influence of supermassive black holes extends to star formation processes within galaxies. At first glance, this might seem surprising. How could an object just a few light years across affect the birth of stars throughout a galaxy spanning tens of thousands of light years? The answer lies in the black hole's ability to influence the gas that serves as the fuel for star formation. During active phases, the energy output from a feeding supermassive black hole can heat the surrounding gas, increasing its pressure and preventing it from collapsing under gravity to form new stars. In extreme cases, the radiation pressure and particle outflows can expel gas entirely from the galaxy's central regions, or even from the galaxy as a whole, effectively shutting down star formation by removing its necessary ingredient. This process helps explain one of the long-standing puzzles in galaxy evolution: why the most massive galaxies in the universe tend to be red and dead, containing primarily older stars with little ongoing star formation. Theoretical models and computer simulations suggest that as these galaxies grew to very large masses, their central black holes also grew, eventually becoming powerful enough to expel or heat most of the gas that would otherwise form new stars. This quenching of star formation appears to be a key step in the evolution of massive elliptical galaxies, driven primarily by black hole feedback. The relationship works in the other direction as well, with galactic processes influencing the growth and activity of the central black hole. Major events in a galaxy's life, such as mergers with other galaxies or interactions with dense intergalactic gas, can funnel large amounts of gas toward the galactic center, feeding the black hole and triggering periods of intense activity. These events help synchronize the growth of the black hole with the evolution of its host galaxy, maintaining the observed correlations between their properties. One of the most dramatic examples of black hole galaxy coevolution occurs during the quasar phase, typically triggered by the merger of two gas-rich galaxies. As the galaxies collide, gravitational torques drive gas toward the center, where it forms a dense disk around the black hole. The resulting accretion releases enormous amounts of energy, creating a quasar that can outshine the entire host galaxy. The radiation and outflows from this active phase can then expel the remaining gas, terminating both the quasar activity and star formation, and leaving behind a more massive black hole at the center of what evolves into an elliptical galaxy. This scenario, often called the quasar mode of galaxy evolution, helps explain the observed properties of massive elliptical galaxies and their central black holes. It suggests that many of these systems passed through a quasar phase earlier in cosmic history, during which their central black holes grew rapidly while simultaneously shaping the future evolution of their hosts by expelling gas and suppressing further star formation. The relationship between supermassive black holes and their host galaxies becomes particularly evident when we examine the population of galaxies as a whole. Galaxies fall into distinct categories based on their properties, with clear correlations between their mass, shape, color, star formation rate, and central black hole characteristics. This organization suggests that galaxy evolution follows certain pathways, with supermassive black holes playing a key role in determining which path a particular galaxy takes. For example, the population of galaxies shows a bimodal distribution in color, with a blue cloud of star-forming spiral and irregular galaxies, and a red sequence of primarily elliptical galaxies with little ongoing star formation. The transition between these populations appears to involve a quenching process in which star formation is shut down, and black hole feedback is a leading candidate for the mechanism behind this transformation in massive galaxies. The densest environments in the universe, galaxy clusters, provide particularly clear evidence of the impact of supermassive black holes on their surroundings. These enormous structures contain hundreds or thousands of galaxies embedded in a hot, diffuse gas with temperatures of millions of degrees. At the center of most clusters lies a massive elliptical galaxy, often called the brightest cluster galaxy, harboring a supermassive black hole that can weigh tens of billions of times the mass of our Sun. Observations with X-ray telescopes reveal that the hot gas permeating these clusters often contains large bubbles or cavities, typically aligned with the jets emitted from the central galaxy's black hole. These structures, sometimes extending for hundreds of thousands of light years, represent regions where the energetic jets have pushed aside the hot gas, creating low-density bubbles. The energy required to create these structures is enormous, equivalent to billions of supernovae, yet the central black hole produces this energy through the efficient conversion of infalling matter into outflowing jets. This process, known as radio mode or maintenance mode feedback, plays a crucial role in regulating the temperature of the cluster gas. Without this energy input, the hot gas would gradually cool and flow toward the cluster center in what's called a cooling flow, leading to excessive star formation and black hole growth in the central galaxy. The jet-driven bubbles effectively heat the gas through various mechanisms, including shock waves, turbulence, and the thermalization of the bubble's energy as they rise through the cluster, preventing this cooling flow and maintaining the observed properties of the cluster over billions of years. The relationship between supermassive black holes and star formation presents a fascinating paradox. On galactic scales, black hole feedback often suppresses star formation by heating or expelling the gas necessary for stars to form. Yet on smaller scales, the same processes can sometimes enhance star formation. The compression of gas by outflows or jets can increase its density, potentially triggering star formation in certain regions. This dual nature of black hole influence, both creative and destructive, highlights the complex relationship between these cosmic beasts and their host galaxies. In our own Milky Way, the central supermassive black hole Sagittarius A star is currently relatively quiet, accreting matter at just a tiny fraction of its theoretical maximum rate. However, there's evidence that it has experienced more active phases in the relatively recent astronomical past. The presence of the Fermi bubbles, large structures extending above and below the galactic plane, detected in gamma rays by the Fermi Space Telescope, suggests an outburst from Sagittarius A star a few million years ago, which may have influenced the evolution of the inner regions of our galaxy. Looking to the future, our understanding of the role supermassive black holes play in galaxy evolution will continue to deepen with new observations and more sophisticated computer simulations. The James Webb Space Telescope, launched in December 2021, will provide unprecedented views of distant galaxies and their central black holes, potentially revealing how this relationship evolved throughout cosmic history. Future gravitational wave observatories like LISA will detect the mergers of supermassive black holes across the universe, offering new insights into this crucial aspect of galaxy evolution. As we've seen, the relationship between supermassive black holes and their host galaxies represents one of the most important aspects of cosmic evolution. Far from being mere passengers in galaxies, these black holes actively shape their environments through the enormous energy they release when accreting matter. The precise balance between black hole growth, star formation, and gas dynamics determines the ultimate fate of a galaxy, whether it becomes a massive elliptical with little ongoing star formation, remains a star-forming spiral, or follows some intermediate path. The story of supermassive black holes and galaxies is one of co-evolution, with each influencing the development of the other throughout cosmic history. This relationship helps explain the remarkable order we observe in the galaxy population, with clear correlations between seemingly unrelated properties. By understanding how supermassive black holes shape their host galaxies, we gain insights not just into these exotic objects themselves, but into the fundamental processes that have sculpted the visible universe into the form we observe today. As we continue our exploration of supermassive black holes, we turn next to a crucial question: how do astronomers actually detect and study objects that, by their very nature, emit no light? The answer involves some of the most innovative observational techniques in modern astronomy, allowing us to probe the darkness at the centers of galaxies and reveal the invisible beasts that lurk there. How do you detect something that, by its very definition, emits no light? This is the fundamental challenge astronomers face when studying supermassive black holes. These cosmic behemoths trap all radiation within their event horizons, making direct observation seemingly impossible. Yet despite this inherent invisibility, scientists have developed ingenious methods to not only confirm the existence of supermassive black holes, but to measure their masses, spins, and other properties with remarkable precision. The quest to detect supermassive black holes relies on a fundamental principle. While we cannot see the black holes themselves, we can observe their profound influence on surrounding matter, energy, and even the fabric of space-time itself. Like detecting an invisible person sitting in a chair by observing the depression in the cushion, astronomers detect black holes by observing their gravitational effects on their cosmic environments. One of the earliest and still most reliable methods for detecting supermassive black holes involves studying the motion of stars and gas near the centers of galaxies. In our own Milky Way, astronomers have spent decades tracking the orbits of individual stars in the central region, an area known as Sagittarius A star. These observations, pioneered by teams led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute, revealed stars moving at extraordinary speeds along elliptical orbits around an unseen central object. The star S2, in particular, follows an elliptical orbit that brings it within just 17 light hours of the galactic center, about 4 times the distance from our Sun to Neptune, while traveling at speeds up to 7,600 kilometers per second, or about 2.5% of the speed of light. The only explanation for such rapid orbital motion is the presence of an extremely compact, massive object, a supermassive black hole with a mass of about 4.3 million suns. This work, which earned Ghez and Genzel a share of the 2020 Nobel Prize in Physics, provided the most conclusive evidence yet for the existence of supermassive black holes. By precisely mapping the orbits of multiple stars over many years, astronomers determined not just the mass of Sagittarius A star, but also its size. confirming that the object is far too dense to be anything other than a black hole. While directly observing individual stars works well for our own galaxy, the centers of most other galaxies are too distant for us to resolve individual stellar orbits. For these more distant systems, astronomers turn to spectroscopy, the study of how matter absorbs and emits light at different wavelengths. By analyzing the spectrum of light from a galaxy's center, scientists can determine how fast the stars and gas are moving. In a technique called stellar velocity dispersion measurement, astronomers analyze the collective motion of stars in a galaxy's central bulge. The presence of a supermassive black hole creates a distinctive pattern in which stars near the center move much faster than would be expected based solely on the visible mass of stars. By measuring this velocity dispersion and applying models based on orbital dynamics, astronomers can infer the mass of the central black hole. Another spectroscopic technique focuses on rotating disks of gas found at the centers of many galaxies. As this gas orbits the central black hole, the side moving toward us appears slightly blue-shifted, its light waves compressed to shorter wavelengths, while the side moving away appears red-shifted, its light waves stretched to longer wavelengths. The magnitude of this effect reveals the rotation speed, which in turn indicates the mass of the central object. For this method to work effectively, astronomers need high spatial resolution to measure the rotation very close to the black hole, where its gravitational influence dominates over the collective pull of all the stars. Some supermassive black holes announce their presence more dramatically through their feeding activity. When substantial amounts of gas fall toward a black hole, the material forms a rotating accretion disk that heats up to millions of degrees due to friction and compression. This superheated plasma emits enormous amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, creating what astronomers call an active galactic nucleus, or AGN. The most powerful AGNs, known as quasars, can outshine their entire host galaxies, making them visible across billions of light years. The energy output of these objects is so immense that it can only be explained by the extremely efficient conversion of matter to energy that occurs in the deep gravitational well of a supermassive black hole. The first quasars were discovered in the 1960s as radio sources that appeared star-like in optical images, hence the name quasi-stellar radio source or quasar. But their true nature as distant, actively feeding supermassive black holes wasn't recognized until later. Studying the properties of AGNs provides valuable information about the black holes powering them. The brightness fluctuations, spectrum, and energy distribution of the emitted radiation can reveal the black hole's mass, spin, and accretion rate. A technique called reverberation mapping measures the time delay between fluctuations in the light from the inner accretion disk and corresponding changes in gas clouds orbiting farther out. This time delay, combined with the speed of light, allows astronomers to determine the size of the region and thus estimate the black hole's mass. Some actively feeding black holes produce powerful jets of particles, accelerated to nearly the speed of light. These relativistic jets, visible primarily at radio wavelengths, can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of the host galaxy. The presence of such jets provides strong evidence for a supermassive black hole, as only the enormous energy released by matter falling into such an object can accelerate particles to these extreme velocities. Radio observations of these jets have played a crucial role in the study of supermassive black holes. The technique of very long baseline interferometry, VLBI, combines signals from radio telescopes across the globe to create a virtual telescope with the resolving power of an Earth-sized dish. This allows astronomers to probe structures very close to the central black hole, revealing the launch regions of jets and the dynamics of the surrounding accretion flow. The ultimate extension of the VLBI technique led to one of the most remarkable achievements in the history of black hole astronomy, the first direct image of a black hole's shadow. In April 2019, the Event Horizon Telescope collaboration unveiled an image of the supermassive black hole at the center of the galaxy Messier 87. located about 55 million light-years from Earth. This black hole, with a mass of about 6.5 billion suns, appears as a dark circular shadow surrounded by a bright ring of light. This groundbreaking image was the result of observations from 8 radio telescopes spread across the globe, working together as a single Earth-sized observatory. The resolution achieved was equivalent to being able to read a newspaper in New York from a sidewalk cafe in Paris. The image shows not the black hole itself, which emits no light, but rather its shadow, the light-trapping region created by the extreme bending of space-time around the black hole, surrounded by the glowing hot gas of the accretion disk. In 2022, the same team released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Despite being more than 1,000 times less massive than the Messier 87 black hole, Sagittarius A star is also about 1,000 times closer to Earth, meaning the two objects appear roughly the same size in the sky. The image reveals a similar ring structure, confirming that this object shares the fundamental properties expected of a supermassive black hole. These direct images represent the culmination of decades of theoretical and observational work, providing visual confirmation of the existence of event horizons, the defining feature of black holes. The size and shape of the shadow match precisely with the predictions of Einstein's general theory of relativity, providing some of the most stringent tests yet of this cornerstone of modern physics. Beyond electromagnetic radiation, black holes can be detected through an entirely different phenomenon: gravitational waves. These ripples in the fabric of space-time are produced when massive objects accelerate, with the strongest waves coming from the collision and merger of black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves from the merger of two stellar mass black holes, opening a new window on the universe. While current gravitational wave detectors like LIGO and Virgo are primarily sensitive to the mergers of stellar mass black holes, future space-based observatories like the Laser Interferometer Space Antenna, LISA, will be able to detect the gravitational waves produced when supermassive black holes merge following galaxy collisions. These observations will provide entirely new insights into the populations, masses, and spins of supermassive black holes throughout the universe, independent of their electromagnetic emissions. Another method for detecting supermassive black holes involves gravitational lensing, the bending of light from background sources as it passes through the curved spacetime near a massive object. When light from a distant galaxy or quasar passes near a foreground galaxy containing a supermassive black hole, the gravity of the black hole and its host galaxy can create multiple images of the background source, sometimes forming complete or partial rings of light. By carefully analyzing these lensed images, astronomers can construct detailed models of the mass distribution in the lensing galaxy, potentially revealing the presence and properties of its central black hole. While this technique has been used primarily to study the overall mass distribution in galaxies and galaxy clusters, future observations with the next generation of telescopes may allow more direct measurements of individual supermassive black holes through their lensing effects. Some of the most compelling evidence for supermassive black holes comes from observations of tidal disruption events, the dramatic destruction of stars that venture too close to a black hole. When a star approaches within a certain distance, known as the tidal disruption radius, the difference in gravitational pull between the near and far sides of the star becomes so great that it overcomes the star's internal cohesion, tearing it apart into a long stream of gas. About half of this stellar material is flung away from the black hole, while the rest falls back, forming a temporary accretion disk that heats up and emits a characteristic flare of radiation. These flares, which typically peak in ultraviolet and X-ray wavelengths, can outshine the entire host galaxy for weeks or months before gradually fading as the available stellar material is consumed or dispersed. Tidal disruption events provide a unique opportunity to study otherwise dormant black holes. Many supermassive black holes spend most of their time in a quiescent state, with little or no detectable accretion activity. When one of these sleeping giants tears apart a passing star, it briefly lights up, allowing astronomers to detect and study a black hole that would otherwise remain hidden. The properties of the resulting flare, including its brightness, duration, and spectrum, can reveal the black hole's mass and spin. The frequency of tidal disruption events also provides information about the population of supermassive black holes and the dynamics of stars in galactic centers. Current estimates suggest that in a typical galaxy, a star is disrupted by the central black hole roughly once every 10,000 to 100,000 years. With billions of galaxies in the observable universe, astronomers detect several such events each year with current telescopes, and future surveys will likely discover hundreds annually. For black holes in the upper mass range, those with masses above about 100 million solar masses, tidal disruption events become increasingly rare. This is because for very massive black holes, the tidal disruption radius is inside the event horizon for solar-type stars, meaning the star would be swallowed whole rather than torn apart. However, these more massive black holes can still disrupt larger stars or giants, which have lower average densities and thus larger tidal disruption radii. Some of the most exotic evidence for supermassive black holes comes from observations of what are called megamasses. A massa, microwave amplification by stimulated emission of radiation, is the microwave equivalent of a laser, where molecules in a gas, typically water, are stimulated to emit coherent microwave radiation. When these masers occur in the accretion disks around supermassive black holes, they can be extraordinarily bright, allowing precise measurements of the disk's rotation speed and thus the black hole's mass. The most famous example is in the galaxy NGC 4258, where observations of water megamasses reveal a thin, nearly edge-on disk of gas orbiting a central mass of about 3.9 million solar masses. The precision of these measurements is remarkable. The black hole mass is determined to within about 3% uncertainty, making it one of the most precisely measured black hole masses outside our own galaxy. Another promising technique for studying supermassive black holes involves X-ray reflection spectroscopy. When high-energy X-rays from the hot inner regions of an accretion disk strike cooler material farther out, they can be reflected, creating a distinctive spectrum that carries information about the geometry of the system and the properties of the central black hole. In particular, the shape of the iron K-alpha emission line, which appears at an energy of about 6.4 kilo-electron volts, can be dramatically altered by the strong gravitational redshift and relativistic effects near the black hole. By carefully analyzing these distorted emission lines, astronomers can measure not only the black hole's mass, but also its spin, a fundamental property that has profound implications for the black hole's history and its effects on the surrounding environment. The spin of a black hole, which ranges from 0 for a non-rotating black hole to 1 for a maximally rotating one, tells us about how the black hole has grown over time. Black holes that have grown primarily through mergers with other black holes with randomly oriented spins tend to have lower spin values, while those that have grown primarily through orderly accretion of gas tend to have higher spins. The detection of supermassive black holes isn't limited to individual objects. Astronomers also study entire populations of black holes through statistical methods. Surveys of active galactic nuclei across cosmic time reveal how the activity and growth of supermassive black holes have evolved throughout the universe's history. These studies show that quasar activity peaked about 10 billion years ago, during what astronomers call cosmic noon, when the universe was roughly 3 to 4 billion years old. This peak in black hole activity coincides with the peak in star formation across the cosmos, further supporting the idea of co-evolution between supermassive black holes and their host galaxies. By combining observations of black hole activity with measurements of star formation rates, galaxy merger frequencies, and other cosmic processes, astronomers can piece together a comprehensive picture of how supermassive black holes have shaped the evolution of galaxies throughout cosmic history. Looking toward the future, our ability to detect and study supermassive black holes will continue to improve with new observational facilities. The James Webb Space Telescope, launched in December 2021, provides unprecedented infrared sensitivity and spatial resolution, allowing detailed studies of dust-obscured active galactic nuclei and the coevolution of black holes and galaxies in the early universe. Future X-ray observatories with high spectral resolution, such as the proposed Lynx and Athena missions, will revolutionize our understanding of accretion processes and black hole spins. These observatories will be able to trace the hot gas around supermassive black holes with unprecedented detail, revealing the complex flows and feedback mechanisms that connect black holes to their host galaxies. In the radio regime, next-generation, very long baseline interferometry arrays will build on the success of the Event Horizon Telescope, providing even sharper images of black hole shadows and the regions around them. These observations will allow more stringent tests of general relativity in the strong field regime, and potentially reveal new physics at the boundaries of our current understanding. Perhaps the most revolutionary advance will come from gravitational wave astronomy. The planned Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers throughout the observable universe. These observations will provide direct measurements of black hole masses and spins, independent of electromagnetic observations, and will trace the hierarchical growth of black holes through mergers across cosmic time. The combination of these multi-messenger observations, electromagnetic radiation across the spectrum, gravitational waves, and perhaps even neutrinos from certain black hole processes, will provide a comprehensive picture of supermassive black holes that would have been unimaginable just a few decades ago. From their formation in the early universe to their ultimate fate in the distant cosmic future, these observations will continue to unveil the secrets of these cosmic behemoths. As we've seen, the detection of supermassive black holes represents one of the great triumphs of modern astronomy. Despite their intrinsic invisibility, these cosmic giants reveal themselves through their profound influence on their surroundings. From the frantic dance of stars in our galactic center to the brilliant beacons of quasars visible across the cosmos, from the massive jets extending far beyond their host galaxies to the subtle shadows cast against their own accretion disks. Through ingenious observational techniques and the careful application of physical laws, astronomers have not only confirmed the existence of these extraordinary objects, but have begun to understand their properties, histories, and crucial role in shaping the visible universe. Having explored how astronomers detect and study supermassive black holes, we now turn our attention to the most extreme examples known, the largest and most powerful of these cosmic behemoths, whose properties push the boundaries of our understanding of physics and challenge our conceptions of just how extreme the universe can be. In the cosmic hierarchy of black holes, there exists an elite class of true monsters, the ultramassive black holes that represent the most extreme objects in our universe. These cosmic leviathans, with masses ranging from billions to tens of billions of times that of our Sun, push the boundaries of our understanding of physics and challenge our conceptions of how such enormous objects could form within the age of the universe. Let us journey to the realm of these cosmic extremes, where gravity reigns supreme and the very fabric of spacetime is warped beyond our everyday comprehension. The current record holder for the most massive black hole ever discovered resides in the galaxy TON 618, an extremely luminous quasar located about 10.4 billion light-years from Earth. This cosmic giant contains a staggering mass estimated at 66 billion solar masses, equivalent to about 14,000 times the mass of the black hole at the center of our Milky Way galaxy. Discovered in 2019 by a team led by astronomer Kianush Mergan, using data from the European Southern Observatory's Very Large Telescope, This behemoth represents the upper extreme of what we currently know exists in our universe. What makes TON 618's black hole particularly remarkable is not just its enormous mass, but also when it existed. The light we observe from this distant quasar began its journey toward Earth when the universe was only about 3.2 billion years old, less than a quarter of its current age. This means that this ultra-massive black hole had already accumulated its enormous mass relatively early in cosmic history, raising profound questions about how such an object could grow so large so quickly after the Big Bang. The event horizon of this cosmic titan would span a region larger than our entire solar system. If placed at the center of our solar system, its event horizon would extend well beyond the orbit of Pluto, engulfing all the planets and countless smaller bodies in our cosmic neighborhood. Yet despite this enormous size, the average density within its event horizon would be relatively low, comparable to water or even air, due to the mathematical relationship between a black hole's mass and its volume. Not far behind TON 618 in the cosmic weight class is the ultramassive black hole at the center of the galaxy Holmberg 15A, a supergiant elliptical galaxy located about 700 million light-years from Earth. This cosmic giant, studied in detail by a team led by Jens Thomas of the Max Planck Institute for Extraterrestrial Physics, contains an estimated 40 billion solar masses, concentrated in a region smaller than our solar system. What makes the Holmberg 15 a black hole particularly interesting is its unusual quietness given its enormous mass. Unlike TON 618, which blazes across the cosmos as a brilliant quasar, the black hole in Holmberg 15A is relatively dormant, accreting matter at a much lower rate. This difference illustrates an important aspect of supermassive black holes. Their mass doesn't necessarily correlate with their current activity level. Some of the most massive black holes in the nearby universe are surprisingly quiet, having perhaps exhausted much of the gas in their vicinity during earlier, more active phases. The galaxy NGC 1277, located about 200 million light-years from Earth in the constellation Perseus, harbors another ultramassive black hole with an estimated mass of between 10 and 40 billion solar masses. This galaxy serves as the central dominant galaxy of the Perseus cluster, one of the most massive structures in the nearby universe, containing thousands of galaxies bound together by gravity. The black hole at the center of NGC 1277 has created some of the most powerful relativistic jets observed in the universe. These jets, extending for hundreds of thousands of light-years, have carved out enormous bubbles in the hot gas that permeates the Perseus cluster. The energy required to create these structures is staggering, equivalent to hundreds of billions of supernovae. Yet the black hole produces this energy through the efficient conversion of infalling matter into outflowing jets. Radio observations of NGC 1277 reveal that these jets emit a deep, resonant note, a pressure wave with a frequency corresponding to a B-flat, albeit about 57 octaves below middle C, far too deep for human hearing. This cosmic bass note, detected as pressure waves rippling through the hot cluster gas, represents one of the ways that supermassive black holes can influence their surroundings on truly enormous scales, helping to prevent the cooling and collapse of gas throughout the cluster. Another cosmic heavyweight is the black hole at the center of the galaxy, IC 1101, which lies about 1.2 billion light-years from Earth. With an estimated mass of 40 billion solar masses, this supermassive black hole resides in what might be the largest galaxy in the observable universe. IC 1101 spans about 5.5 million light-years in diameter, more than 50 times the size of our Milky Way, and contains a mass equivalent to about 100 trillion suns. The sheer scale of IC 1101 and its central black hole illustrates the close relationship between galaxy size and black hole mass. The largest galaxies typically host the largest black holes, following the scaling relationships we discussed earlier. IC 1101 likely grew to its enormous size through multiple mergers with other galaxies, and its central black hole similarly grew by consuming both gas and other black holes during these cosmic collisions. Moving closer to home, the giant elliptical galaxy Messier 87, located about 55 million light-years from Earth in the Virgo cluster, harbors a supermassive black hole with a mass of about 6.5 billion solar masses. While not the most massive known, this black hole holds a special place in astronomical history as the first to be directly imaged by the Event Horizon Telescope in 2019. The iconic image of the Messier 87 black hole shows a bright ring of light surrounding a dark central shadow, the light-trapping region created by the extreme bending of spacetime around the black hole. The ring appears brighter on one side due to the Doppler boosting of light from the part of the accretion disk that is rotating toward us, providing visual confirmation of the black hole's rotation. This groundbreaking observation not only confirmed the existence of black holes as predicted by Einstein's theory of general relativity, but also opened a new era in the direct study of these cosmic extremes. The Messier 87 black hole is also noteworthy for its powerful relativistic jet, which extends for thousands of light-years from the galaxy's center. This jet, visible primarily at radio wavelengths, consists of particles accelerated to nearly the speed of light by the intense magnetic fields near the black hole. The energy carried by this jet influences the evolution of the entire galaxy and its surroundings, illustrating the outsized impact that supermassive black holes can have on their cosmic environments. Beyond these individual record holders, astronomers have identified a class of objects called ultramassive black holes, those with masses exceeding 10 billion solar masses. A comprehensive study published in 2012 by astronomer Nicholas McConnell and colleagues identified about a dozen such objects in nearby galaxies, suggesting that these cosmic titans, while rare, are more common than previously thought. These ultramassive black holes are typically found in brightest cluster galaxies, the largest, most luminous galaxies located at the centers of massive galaxy clusters. Their enormous masses likely result from a combination of processes, including efficiently consuming gas during the early universe, when it was more abundant, and growing through mergers with other black holes during galaxy collisions. Their current relatively dormant state reflects the depletion of gas in their host galaxies, limiting further growth through accretion. The true upper limit to black hole mass remains an open question in astrophysics. Theoretical arguments suggest that black holes in the early universe might have been limited to masses of about 50 billion solar masses due to the interaction between their radiation output and the surrounding gas. As the black hole grows and emits more radiation, it eventually pushes away the very gas that fuels its growth, creating a self-limiting process. However, this limit could potentially be exceeded through black hole mergers or in environments with particularly high gas densities. Some theoretical models suggest that black holes with masses of 100 billion solar masses or even larger could exist, particularly in the densest regions of the universe. Future observations with more sensitive instruments may yet discover black holes that surpass the current record holders. Beyond their enormous masses, what makes these ultramassive black holes particularly fascinating is their power output when actively accreting matter. Quasars, the most luminous persistent sources of energy in the universe, are powered by supermassive black holes in the process of consuming substantial amounts of gas. The most powerful quasars, typically powered by black holes with masses of billions to tens of billions of solar masses, can outshine their entire host galaxies by factors of hundreds or even thousands. The quasar APM 08279 +5 255, one of the most luminous objects known, emits energy equivalent to more than 10 trillion suns, despite being powered by a black hole that, while massive, is not among the very largest known. This extraordinary efficiency in converting matter to energy, about 10 to 100 times more efficient than nuclear fusion, is a hallmark of black hole accretion, where gravitational potential energy is converted to radiation as matter spirals into the black hole's intense gravitational field. The most powerful quasars can influence regions spanning millions of light-years, far beyond the boundaries of their host galaxies. The radiation and particle outflows from these cosmic beacons heat and push away surrounding gas, profoundly affecting the evolution of their host galaxies and even neighboring systems. In the most extreme cases, quasar outflows can expel gas from entire galaxy clusters, effectively shutting down star formation across regions spanning millions of light years. The energy output of the most powerful quasars also makes them visible across vast cosmic distances. The current record holder for the most distant known quasar, J0313-1806, is observed as it existed just 670 million years after the Big Bang, when the universe was less than 5% of its current age. Despite its tremendous distance, more than 13 billion light-years, this quasar is bright enough to be detected by current telescopes, thanks to the enormous energy output of its central black hole, estimated at about 1.6 billion solar masses. The existence of such massive black holes so early in cosmic history represents one of the most significant challenges to our understanding of black hole formation and growth. The conventional processes of black hole growth through accretion seem too slow to explain how billion solar mass black holes could form within the first billion years after the Big Bang. This timing problem has led astronomers to explore alternative formation scenarios, including the direct collapse of massive gas clouds in the early universe, or periods of super Eddington accretion, where black holes grow faster than standard physical limits would suggest. Beyond their masses and energy outputs, the largest black holes also shape their surroundings through their gravitational influence, creating unique structures in the centers of their host galaxies. In many giant elliptical galaxies, observations reveal a central region where the density of stars is lower than would be expected based on the overall distribution of stars in the galaxy. These cores, or missing light regions, are thought to result from the gravitational interactions between binary supermassive black holes following galaxy mergers. When two galaxies merge, their central black holes eventually form a binary system that ejects nearby stars through gravitational interactions. This process, sometimes called gravitational slingshot, can remove a substantial amount of stellar mass from the galactic center, creating the observed cores. The size of these cores correlates with the mass of the central black hole, with the largest black holes creating the largest cores. In the most extreme cases, such as in the galaxy NGC 1277, the core radius can extend for thousands of light years, containing missing stellar mass equivalent to billions of suns. The most massive black holes also raise intriguing questions about their ultimate fate in the far cosmic future. As the universe continues to expand and the average density of matter decreases, the rate at which these black holes can accrete new material will steadily decline. Eventually, they will enter an era of effective starvation, accreting only the occasional star or gas cloud that strays too close. Over much longer timescales, far longer than the current age of the universe, even these cosmic giants will begin to lose mass through the quantum process of Hawking radiation, where virtual particle pairs created near the event horizon result in a slow leakage of energy from the black hole. For a black hole with a mass of Ton 618, this evaporation process would take an almost unimaginable amount of time, roughly 10 to the power of 100 years, 1,000 trillion years. This time span is so vast that it exceeds the time needed for even the longest-lived stars to exhaust their nuclear fuel by a factor of many trillions. During this unimaginably long period of evaporation, the black hole would gradually lose mass and shrink in size. At first, the process would be imperceptibly slow, with the black hole losing less than the mass of a proton each year. But as the black hole's mass decreases, the rate of evaporation would accelerate, eventually culminating in a final burst of radiation as the last remnants of the once mighty black hole disappear in a flash of high-energy particles. This final fate, however, lies so far in the future that it has no practical relevance to the evolution of the universe as we observe it today. In the meantime, these cosmic behemoths will continue to influence their surroundings in profound ways. The largest black holes, particularly those at the centers of galaxy clusters, play a crucial role in regulating the temperature and density of the hot gas that permeates these enormous structures. Through their jets and radiation, they inject enormous amounts of energy into their surroundings, preventing the cooling and collapse of gas that would otherwise lead to runaway star formation in the central galaxies. This regulatory role, sometimes called maintenance mode feedback, represents one of the most important large-scale processes in the universe. Without it, the centers of galaxy clusters would look very different. The central galaxies would be much more massive and blue with ongoing star formation, rather than the relatively quiescent, red, elliptical galaxies we observe. The largest black holes thus serve as cosmic thermostats, maintaining the observed properties of the most massive structures in the universe over billions of years. The study of these cosmic extremes pushes the boundaries of our observational capabilities and theoretical understanding. Future facilities, such as the 30-meter class optical telescopes currently under construction and next-generation radio interferometers, will provide even more detailed views of these objects and their surroundings. Space-based gravitational wave detectors like LISA will detect the mergers of these giants across cosmic history, revealing how they grew to their enormous sizes. As we continue to explore these cosmic monsters, the largest, most massive single objects in the universe, we gain insights not just into extreme astrophysics, but into the fundamental nature of gravity, spacetime, and the evolution of cosmic structure. These ultramassive black holes represent nature at its most extreme, showing us what happens when ordinary physics is pushed to extraordinary limits. From TON 61866 billion solar masses to the powerful jets of NGC 1277. From the direct image of Messier 87's shadow to the brilliant beacon of distant quasars, these cosmic behemoths continue to fascinate and challenge our understanding. They represent both the pinnacle of black hole evolution and the most powerful engines in the universe, objects whose influence extends far beyond their immediate surroundings to shape the evolution of galaxies, clusters, and the cosmos itself. Having explored these individual giants, we next turn our attention to what happens when two of these cosmic titans collide. The merger of supermassive black holes represents one of the most energetic events in the universe, releasing enormous amounts of energy in the form of gravitational waves, ripples in the very fabric of space-time that carry away the equivalent of multiple solar masses of energy in a cosmic instant. These mergers, occurring throughout cosmic history following galaxy collisions, have played a crucial role in creating the ultramassive black holes we observe today, and will provide a new window on the universe through future gravitational wave observations. Throughout the cosmos, a slow-motion drama unfolds as galaxies collide and merge. These cosmic encounters, happening countless times across the universe's history, bring together not just stars and gas, but also the supermassive black holes lurking at each galaxy's heart. The result is one of the most extraordinary phenomena in nature, the merger of two supermassive black holes. An event so powerful it literally shakes the fabric of space-time, sending ripples outward at the speed of light that carry away the energy equivalent of millions or billions of stars in a cosmic instant. The journey toward a black hole merger begins with the interaction of their host galaxies. When two galaxies pass close enough to each other, their mutual gravitational attraction can overcome their relative motion, causing them to begin a cosmic dance that may last for hundreds of millions or even billions of years. During this extended interaction, the galaxies may make several close passages before finally merging, their stars and gas clouds experiencing powerful tidal forces that distort their structures, creating spectacular bridges, tails, and shells visible in deep astronomical images. We can witness various stages of this process throughout the nearby universe. The antennae galaxies, located about 65 million light-years from Earth, represent an early stage of a galaxy merger, with two spiral galaxies in the process of colliding, their shapes already significantly distorted by tidal forces. Streams of stars and gas extend outward like antennae, giving the system its name, while regions where gas clouds collide have triggered intense bursts of star formation, visible as bright blue regions in optical images. As the merger progresses, the two galaxies' central regions, each harboring a supermassive black hole, gradually approach each other. Initially separated by tens of thousands of light-years, the black holes begin a journey toward eventual coalescence. This journey proceeds through several distinct phases, each governed by different physical processes and operating on different timescales. In the first phase, the black holes and their surrounding stars approach each other through a process called dynamical friction. As a massive object moves through a field of stars, its gravitational pull causes the stars to form a wake behind it, creating a slight overdensity of mass that pulls backward on the moving object, gradually slowing it down. This process causes both black holes to lose orbital energy and angular momentum, causing them to spiral inward toward the center of the merging galaxy system. Dynamical friction operates most efficiently when the black holes are still separated by hundreds or thousands of light years. As they get closer, within about a few dozen light years of each other, a new phase begins. At this point, the two black holes form a bound binary system, orbiting their common center of mass. The binary continues to lose energy primarily through interactions with nearby stars, which can be gravitationally slingshot away from the system, carrying away energy and angular momentum. This process gradually brings the black holes closer together, but it becomes increasingly inefficient as the separation decreases. The reason is simple. Each interaction with a star can only remove a limited amount of energy from the binary, and as the binary orbit shrinks, it requires stars with very specific trajectories to interact effectively. Eventually, the supply of such stars can be exhausted, potentially stalling the binary at a separation of about 1 light-year, a problem known as the final parsec problem in astrophysics. How binary black holes overcome this barrier remains an active area of research. Several mechanisms have been proposed, including interactions with gas in the galactic center, which can create drag on the black holes, the influence of a non-spherical distribution of stars, which can supply more stars on suitable trajectories, or the presence of a third black hole, which can perturb the binary orbit. Recent computer simulations suggest that in most realistic galactic environments, the final parsec problem can indeed be overcome, allowing the binary to continue its inward spiral. When the black holes finally reach a separation of less than about 1/100th of a light-year, just a few thousand times the size of the event horizons themselves for typical supermassive black holes, a new and remarkable phase begins. At this close distance, the black holes begin to emit significant amounts of energy in the form of gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity. Gravitational waves are, in essence, propagating distortions in space-time itself. They stretch and compress space as they pass through it, alternately increasing and decreasing the distance between objects. These waves travel at the speed of light and carry energy and angular momentum away from their source. For a binary black hole system, the emission of gravitational waves causes the orbit to shrink and circularize, accelerating the inward spiral. The gravitational wave emission becomes increasingly powerful as the black holes approach each other, following an inverse power law with separation. In the final stages, the black holes orbit each other at a significant fraction of the speed of light, completing their last few orbits in minutes or seconds, rather than the millions of years that characterized earlier phases of the merger. The frequency of the emitted gravitational waves increases correspondingly, sweeping upward in what astrophysicists call a chirp, named for its audio analog when the signal is converted to sound. Finally, the black holes merge, their event horizons combining to form a single, more massive black hole. This final merger releases an enormous amount of energy in a powerful burst of gravitational waves. For a merger of two equal mass supermassive black holes, each with 1 billion solar masses, the energy released would be equivalent to converting several billion times the mass of Earth entirely into energy, an amount that dwarfs the total energy output of all the stars in the observable universe during the same brief interval. The merged black hole is initially in a highly distorted state, like a ringing bell or a wobbling droplet of water. It releases this excess energy through gravitational waves in a phase called ringdown, where the distortions are damped out and the black hole settles into its final stable state, characterized by just three parameters: mass, spin, and electric charge, which is typically negligible for astrophysical black holes. Remarkably, the final black hole's mass is slightly less than the sum of the two original black holes' masses. The missing mass, typically around 5% for equal mass mergers with non-spinning black holes, and potentially up to 20% for rapidly spinning black holes with favorable spin alignments, is converted directly into gravitational wave energy according to Einstein's famous equation E equals mc squared. This mass-energy conversion makes black hole mergers among the most efficient energy-producing processes in the universe, far exceeding the roughly 0.7% efficiency of nuclear fusion in stars. While the basic physics of black hole mergers has been understood for decades through analytical approximations, precise calculations of the gravitational waveforms produced during mergers required the development of numerical relativity, the use of supercomputers to solve Einstein's field equations for dynamic, strongly gravitating systems. This breakthrough, achieved in 2005 after decades of effort, allowed scientists to predict exactly what gravitational wave signals from black hole mergers should look like, paving the way for their eventual detection. That detection came in 2015 when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the merger of two stellar mass black holes, about 36 and 29 times the mass of the Sun, located about 1.3 billion light-years from Earth. This groundbreaking observation, which earned the 2017 Nobel Prize in Physics for key LIGO founders, provided the first direct confirmation of both gravitational waves and black holes, opening a new window on the universe. Since that initial detection, LIGO and its European counterpart Virgo have observed dozens more black hole mergers, all involving stellar mass black holes, with masses ranging from a few to about 100 solar masses. These observations have revealed a population of black holes more numerous and massive than previously known from observations of X-ray binaries, providing new insights into the formation and evolution of stellar mass black holes. However, current ground-based gravitational wave detectors are not sensitive to the much lower frequency waves produced by supermassive black hole mergers. To detect these signals, we need space-based detectors, free from the seismic noise and gravity gradient fluctuations that limit ground-based instruments at low frequencies. The primary mission designed for this purpose is the Laser Interferometer Space Antenna, LISA, a constellation of 3 spacecraft flying in a triangular formation, with laser beams measuring the tiny changes in distance between them caused by passing gravitational waves. When launched, currently planned for the mid-2030s, LISA will be sensitive to gravitational waves from supermassive black hole mergers throughout the observable universe. Models predict that LISA might detect anywhere from a few to hundreds of such mergers per year, providing a comprehensive census of black hole mergers across cosmic history and revealing how these objects grew to their current sizes. The waveforms of these gravitational signals will carry detailed information about the merging black holes, including their masses, spins, orbital eccentricities, and even their locations on the sky. By comparing the observed merger rate with theoretical models and computer simulations of galaxy formation and evolution, astronomers will gain new insights into how galaxies and their central black holes have evolved together throughout cosmic history. One particularly intriguing possibility is that LISA might detect mergers involving intermediate mass black holes, objects with masses between 100 and 100,000 solar masses. These objects, which remain largely hypothetical with only a handful of candidate detections, might represent the missing link between stellar mass and supermassive black holes. If they exist in significant numbers, their mergers should produce gravitational waves at frequencies intermediate between those detected by LIGO and those expected from supermassive black hole mergers, potentially falling within LISA's sensitive range. Beyond merely detecting black hole mergers, gravitational waves offer a unique probe of strong field gravity, the behavior of space-time in regions of extreme curvature near black holes. The detailed shape of the gravitational waveform during the final merger and ring-down phases is sensitive to the exact nature of the objects involved. If black holes behave exactly as predicted by Einstein's theory of general relativity, the waveforms should match the predictions of numerical relativity simulations. Any deviations would signal new physics beyond general relativity, potentially providing clues to a quantum theory of gravity. The merger of supermassive black holes also has profound implications for the galaxies that host them. The enormous energy released during the final merger, while primarily in the form of gravitational waves that interact very weakly with matter, can still influence the surrounding stars and gas through more subtle effects. If the merging black holes have unequal masses or misaligned spins, the merged black hole can receive a recoil kick due to asymmetric gravitational wave emission, potentially moving it hundreds or thousands of light years from the galactic center, or, in extreme cases, being ejected from the galaxy entirely. Such recoiling black holes would leave distinctive signatures in their host galaxies, including offset active galactic nuclei, where the bright accretion disk surrounding the black hole appears displaced from the galaxy's center, disturbed stellar distributions, or trails of shocked gas as the black hole plows through the interstellar medium. Several candidate recoiling black holes have been identified, though none have been definitively confirmed. Even without significant recoil, the merger process can profoundly affect the central regions of the host galaxy. As the binary black hole system evolves, it ejects stars from the galactic center through gravitational slingshot interactions, potentially creating a missing light core, a region where the stellar density is lower than would be expected from the overall distribution of stars in the galaxy. The size of this core correlates with the mass of the central black hole, with the largest black holes creating the largest cores, spanning thousands of light years in the most extreme cases. The binary phase can also influence the rate at which the black holes accrete surrounding gas. The orbital motion of the binary creates a low-density gap in any accretion disk surrounding the system, potentially reducing the accretion rate onto both black holes. However, at certain stages, particularly when the black holes are still widely separated, their gravitational perturbations can drive gas inward more efficiently than for a single black hole, potentially triggering enhanced accretion and associated energy output. If sufficient gas is present during the merger process, we might expect to see electromagnetic radiation, light across the spectrum from radio waves to gamma rays, accompanying the gravitational wave emission. This would be a multi-messenger event, providing complementary information about the merger and its environment. The detection of both gravitational waves and electromagnetic radiation from the same event would allow more precise localization of the source and potentially reveal details about the gas environment around the merging black holes. The rates of supermassive black hole mergers throughout cosmic history remain somewhat uncertain, depending on the rates of galaxy mergers and the efficiency with which black hole binaries overcome the final parsec problem. Current estimates suggest that in the nearby universe, mergers of massive black holes with masses above 10 million solar masses occur at a rate of roughly 1 per year, within a volume of 1 cubic gigaparsec, a region containing about 100,000 large galaxies. The rate was likely higher in the past, when galaxy merger rates were higher due to the denser cosmic environment. The growth of black holes through mergers versus accretion of gas remains an active area of research. In the early universe, when gas was abundant, accretion likely dominated the growth process for most black holes. In the present epoch, with lower gas densities in many galaxies, mergers may play a more significant role, particularly for the largest black holes in galaxy clusters, where galaxy merger rates remain relatively high. Computer simulations of cosmic structure formation, incorporating models of black hole growth and feedback, suggest a complex interplay between these processes throughout cosmic history. During periods of intense cosmic activity, such as the peak of star formation around 10 billion years ago, cosmic noon, accretion-dominated black hole growth for most systems. In contrast, during quieter cosmic periods, mergers became relatively more important, particularly for the most massive black holes. The merger history of a supermassive black hole leaves imprints on its final properties, particularly its spin. A black hole that has grown primarily through aligned accretion, where inflowing gas consistently orbits in the same direction, will tend to have a high spin value, approaching the theoretical maximum. In contrast, a black hole that has grown primarily through mergers with other black holes having randomly oriented spins will tend to have a moderate spin value, as successive mergers with differently oriented spins partially cancel out. Measurements of black hole spins through X-ray observations of active galactic nuclei, and in the future, through gravitational wave detections of mergers, will provide valuable insights into the growth history of these objects. Early results suggest a range of spin values for supermassive black holes, supporting the idea that both accretion and mergers have played important roles in their evolution. Galaxy mergers and the resulting black hole mergers have shaped the universe we observe today. Without them, the most massive galaxies and their central black holes could not have grown to their current sizes. The hierarchical assembly of cosmic structure, with smaller objects merging to form larger ones, represents a fundamental aspect of our universe's evolution, driven by the inexorable force of gravity, acting over billions of years. Looking to the future, our own Milky Way galaxy is on a collision course with the neighboring Andromeda galaxy, with the first close approach expected in about 4.5 billion years. This cosmic encounter will eventually lead to the merger of the two spiral galaxies into a single, larger elliptical galaxy, sometimes called Milkomeda by astronomers. The central black holes of the two galaxies, Sagittarius A star in the Milky Way and a similar black hole in Andromeda, will eventually find each other and merge, releasing enormous amounts of gravitational wave energy in the process. By the time this merger occurs, the Sun will have evolved into a red giant and eventually a white dwarf, potentially ending life on Earth unless humanity has found a way to migrate to other star systems. Any advanced civilization still present in the merged galaxy might be able to detect the gravitational waves from the final merger of the two central black holes, witnessing the birth of a new, more massive black hole at the heart of their home galaxy. On the largest cosmic scales, the mergers of supermassive black holes represent a form of cosmic recycling and consolidation. The matter that falls into black holes isn't truly lost, but rather concentrated into these extraordinarily dense objects, while the energy released during mergers, primarily in the form of gravitational waves, ripples outward through the universe, subtly influencing the fabric of spacetime itself. Over the vast expanse of cosmic time, from the formation of the first black holes shortly after the Big Bang to the distant future when star formation ceases and galaxies grow dark, these mergers will continue, creating ever more massive black holes as the universe ages. The study of black hole mergers thus connects many aspects of astrophysics and cosmology, from the small-scale physics of strong gravity and accretion processes to the large-scale evolution of galaxies and cosmic structure. With new observational facilities coming online in the coming decades, including space-based gravitational wave detectors like LISA and next-generation electromagnetic observatories across the spectrum, our understanding of these cosmic collisions will continue to deepen, revealing new insights into the extraordinary objects that lurk at the centers of galaxies and the role they play in shaping our universe. Having explored what happens when black holes actively merge, we next turn our attention to the opposite end of the activity spectrum, dormant supermassive black holes, the sleeping giants that lurk quietly at the centers of many galaxies, including our own. These objects, while currently accreting matter at very low rates, harbor the potential for renewed activity if their cosmic slumber is disturbed by an influx of gas or the tidal disruption of a passing star. Understanding these dormant phases, which characterize the majority of supermassive black holes in the present-day universe, is crucial for developing a complete picture of black hole evolution throughout cosmic history. While quasars and active galactic nuclei showcase black holes at their most energetic and visible, the majority of supermassive black holes in our present-day universe exist in a far quieter state. These dormant or quiescent black holes, though less spectacular in their energy output, are far more common and represent an essential phase in the life cycle of these cosmic objects. Like slumbering dragons, these sleeping giants lie in wait at the centers of most galaxies, including our own Milky Way. Their immense gravitational power temporarily subdued, but never truly extinguished. What exactly makes a supermassive black hole dormant? The key factor is its accretion rate, the amount of matter it consumes over time. A typical active galactic nucleus might accrete matter at a substantial fraction of the Eddington limit, the theoretical maximum rate determined by the balance between gravitational pull and radiation pressure. In contrast, dormant black holes accrete at rates thousands or even millions of times lower, consuming just tiny wisps of gas from their surroundings rather than the torrential flows that feed their active counterparts. This dramatic difference in feeding rate leads to an equally dramatic difference in energy output. While an active supermassive black hole might outshine its entire host galaxy, a dormant one contributes negligibly to the galaxy's overall luminosity, making it much harder to detect. Without the brilliant accretion disks and broad emission lines that signal active black holes, astronomers must rely on more subtle clues to confirm the presence of these sleeping giants. Our own galactic center hosts perhaps the most well-studied dormant supermassive black hole, known as Sagittarius A star. Located about 26,000 light-years from Earth, this cosmic behemoth contains about 4.3 million solar masses, yet it currently accretes matter at less than 1/1,000,000th of the Eddington limit. Its energy output is so modest that if it weren't for its gravitational influence on surrounding stars, we might not know it exists at all. The evidence for Sagittarius A star comes primarily from the orbits of stars in the galactic center, which trace elliptical paths around an unseen central mass. The star S2, which follows a 16-year orbit that brings it within just 17 light hours of the central object, has been particularly valuable for determining the mass and size of Sagittarius A star. These observations, combined with radio and infrared studies of the galactic center, provide compelling evidence for a supermassive black hole that, while currently quiet, dominates the gravitational landscape of the inner galaxy. What causes a supermassive black hole to enter a dormant phase? The primary factor is simply a lack of fuel. Black holes cannot actively feed without a steady supply of matter, typically in the form of gas, dust, or occasionally unfortunate stars that venture too close. When this fuel supply dwindles, perhaps exhausted by previous periods of activity or expelled by energetic outflows, the black hole's accretion rate drops dramatically, and it enters a quiescent phase. This transition from active to dormant status appears to be a natural part of black hole evolution in many galaxies. Studies of quasar populations across cosmic time reveal that these extremely luminous objects were much more common when the universe was younger, peaking in number around 10 billion years ago. Since then, the overall rate of black hole activity has declined significantly, suggesting that many once brilliant quasars have gradually dimmed as their fuel supplies diminished, eventually becoming the dormant black holes we observe in present-day galaxies. The cycle between active and dormant phases can occur multiple times throughout a supermassive black hole's life. A previously quiet black hole might be awakened by an influx of fresh gas, perhaps delivered by a galaxy merger, the capture of a gas-rich dwarf galaxy, or even internal processes within the host galaxy that funnel gas toward the center. This could trigger a new active phase lasting millions or even hundreds of millions of years before the fuel supply once again dwindles and the black hole returns to dormancy. Even in their dormant state, supermassive black holes continue to exert profound influence through their immense gravity. The very structure of the galactic bulge, the spherical concentration of stars at the center of spiral galaxies like our Milky Way, is shaped by the gravitational pull of the central black hole. The The velocities and orbits of stars throughout the central region bear the imprint of the black hole's presence, even when it's not actively feeding. Detecting dormant black holes presents a significant observational challenge. Without the bright emission that characterizes active nuclei, astronomers must rely on indirect methods, primarily the gravitational influence on surrounding stars and gas. For nearby galaxies, high-resolution observations can reveal the rapid orbital motion of stars or gas clouds near the galactic center, allowing estimation of the central mass. If this mass is too large and concentrated to be explained by stars alone, a supermassive black hole is the likely explanation. Another approach involves searching for low-level activity that might reveal a black hole's presence. Even dormant black holes typically accrete some matter, albeit at very low rates, potentially producing weak radio, infrared, or X-ray emission that can be detected with sensitive instruments. Sagittarius A star, for instance, exhibits variable emission across these wavelengths, indicating that it's not completely inactive, but rather feeding at a minimal level. Recent advances in observation techniques have revealed that truly inactive black holes are rare. Most dormant black holes actually maintain some level of activity, just orders of magnitude lower than their more energetic counterparts. This has led to the concept of a continuous spectrum of black hole activity, from the most brilliant quasars to the barely flickering embers of the most quiescent objects, rather than a simple binary distinction between active and dormant states. The gas surrounding dormant black holes exists in a different physical state than around active ones. Near an active black hole, the intense radiation ionizes the surrounding gas, creating a characteristic emission spectrum with broad and narrow lines. In contrast, the gas near a dormant black hole remains largely neutral or only weakly ionized, producing a very different spectral signature. X-ray observations can sometimes detect hot, diffuse gas in the vicinity of dormant black holes, providing another clue to their presence. One particularly interesting feature found around some dormant supermassive black holes is a circumnuclear disk, a relatively cool, rotating structure of gas and dust extending several light-years from the central black hole. These disks, observed in galaxies like NGC 1277 and our own Milky Way, contain significant amounts of molecular gas and dust, providing a potential reservoir of fuel that could trigger renewed activity if disturbed and driven inward toward the black hole. Even in their dormant state, supermassive black holes occasionally experience brief periods of enhanced activity. These mini outbursts might occur when the black hole captures a small gas cloud or strips material from the outer layers of a star that passes too close without being completely disrupted. Such events can cause temporary increases in the black hole's emission, visible as flares in X-ray, infrared, or radio observations, before the system returns to its quiescent state. In our own galactic center, Sagittarius A star has exhibited several such flares, with its X-ray emissions sometimes increasing by factors of tens or even hundreds for brief periods before returning to its baseline level. These events provide valuable opportunities to study the physics of accretion in the low-rate regime and to probe the environment immediately surrounding the black hole. More dramatic and rare are tidal disruption events, where a star passes close enough to the black hole to be torn apart by tidal forces. For a dormant black hole, such an event represents a temporary feeding frenzy, with a significant fraction of the stellar material forming an accretion disk that heats up and emits brightly across the electromagnetic spectrum. These flares, which typically rise to peak brightness within weeks and fade over months or years, can temporarily increase a dormant black hole's luminosity by factors of thousands or even millions. Several dozen tidal disruption events have been detected to date, primarily through wide-field optical and UV surveys, with follow-up observations across multiple wavelengths. These events provide a unique opportunity to study otherwise invisible dormant black holes as they briefly light up, revealing information about their masses, spins, and surrounding environments. The frequency of these events also offers insights into the dynamics of stars in galactic centers and the population of dormant black holes throughout the universe. What might cause a dormant black hole to fully reawaken and enter a sustained active phase? The most dramatic trigger would be a galaxy merger, where the collision between two galaxies drives large amounts of gas toward their centers, providing fresh fuel for the central black holes. This process, which simultaneously triggers intense bursts of star formation, has been observed in various stages in nearby interacting galaxies and is believed to be a primary driver of black hole activity throughout cosmic history. Internal processes within galaxies can also channel gas toward the center, potentially awakening a dormant black hole. Gravitational instabilities in the form of bars or spiral arms can remove angular momentum from gas, causing it to flow inward. Similarly, stellar feedback from supernovae or intense star formation can disturb gas, potentially driving some of it toward the galactic center. These processes operate more gradually than galaxy mergers, but may be important for sustaining lower levels of black hole activity over extended periods. Observations of galaxies across cosmic time suggest a complex relationship between star formation and black hole activity. In many cases, these processes appear to be triggered by the same events and proceed in parallel, with black holes entering active phases at roughly the same time that their host galaxies experience elevated star formation rates. However, there's often a time delay, with peak black hole activity following peak star formation by tens or hundreds of millions of years, suggesting that the same gas that initially formed stars eventually finds its way to the central black hole. The cycling between active and dormant phases appears to be a fundamental aspect of supermassive black hole evolution. This cycle, sometimes called the AGN duty cycle, varies depending on the black hole's mass, its host galaxy's properties, and the larger cosmic environment. In dense galaxy clusters, for instance, the central dominant galaxies often contain black holes that cycle between active and dormant phases on timescales of tens to hundreds of millions of years, with each active phase triggered by cooling gas from the intracluster medium and shut down when the resulting energy output heats the gas, temporarily cutting off the fuel supply. Evidence for past activity in currently dormant black holes can sometimes be found in their surroundings. Radio observations of our Milky Way have revealed large bubbles of emission extending thousands of light-years above and below the galactic plane, suggesting that Sagittarius A star was much more active in the past, perhaps a few million years ago. Similar structures have been observed in other galaxies with currently dormant central black holes, providing a fossil record of their more active past. In some cases, more direct evidence links currently dormant black holes to past activity. Light echoes, the delayed reflection or reprocessing of light from a past outburst, can reveal activity that occurred hundreds or thousands of years ago. In the galaxy IC 2497, for instance, light echoes observed in gas clouds thousands of light-years from the center suggest that the currently dormant central black hole was a brilliant quasar just 70,000 years ago, having since decreased in luminosity by a factor of at least 10,000. These observations challenge our understanding of how quickly supermassive black holes can transition between active and dormant states. While some theoretical models suggest that such transitions should take millions of years, corresponding to the viscous timescale of a standard accretion disk, the observed rapid changes in some systems point to more complex accretion flows, perhaps involving multiple components with different physical properties and characteristic timescales. The future of currently dormant black holes depends largely on the future evolution of their host galaxies. For isolated galaxies with dwindling gas reserves, like many massive elliptical galaxies, their central black holes may remain dormant indefinitely, occasionally capturing small gas clouds or disrupting stars, but never again reaching the brilliant quasar phase. In contrast, black holes in gas-rich environments or in galaxies likely to experience future mergers may cycle between dormant and active phases for billions of years to come. In our own Milky Way, the future holds a dramatic fate for Sagittarius A star. In about 4.5 billion years, our galaxy will collide with the neighboring Andromeda galaxy, beginning a merger process that will ultimately combine the two spiral galaxies into a single, larger elliptical galaxy. During this process, the central black holes of the two galaxies will eventually find each other and merge, potentially after a period of increased activity as gas disturbed by the collision flows toward the galactic center. The current dormancy of most supermassive black holes has important implications for galaxy evolution in the present-day universe. Without the intense energy output associated with active phases, these black holes exert less immediate influence on star formation and gas dynamics in their host galaxies. However, their gravitational influence remains constant, and the threat of renewed activity ensures that their presence continues to shape the evolution of galaxies over cosmic time. From an observational perspective, the prevalence of dormant black holes presents both challenges and opportunities. While active black holes announce their presence with brilliant radiation across the electromagnetic spectrum, dormant ones require more subtle detection methods, often involving detailed dynamical studies of their host galaxies. However, when a dormant black hole briefly lights up during a tidal disruption event or similar phenomenon, it provides a valuable glimpse into an otherwise hidden population, offering insights into black hole demographics and the dynamics of galactic centers. Understanding the transition between active and dormant phases also has important implications for our models of cosmic evolution. The observed decline in quasar activity over the past 10 billion years must be explained by either a widespread transition to dormancy among previously active black holes, a decrease in the efficiency with which they convert accreted mass into radiation, or some combination of these factors. By studying dormant black holes and comparing them with their more active counterparts, astronomers gain insights into this cosmic downturn and its implications for the future evolution of galaxies. The sleeping giants at the centers of galaxies represent a fascinating chapter in the life story of supermassive black holes. Though currently quiet, they harbor the potential for renewed activity if circumstances change, with profound implications for their host galaxies. Their dormant state, far from being a cosmic endpoint, is merely one phase in an ongoing cycle of activity that shapes the evolution of galaxies throughout cosmic history. As we continue our exploration of supermassive black holes, we next turn to a mysterious connection that links these extraordinary objects to one of the greatest puzzles in modern physics: dark matter. Though fundamentally different in nature, one being the densest form of ordinary matter, the other being an unseen substance that interacts primarily through gravity, black holes and dark matter appear to be deeply connected, influencing each other's distribution and evolution throughout the cosmos. This relationship, still not fully understood, provides tantalizing clues about the formation of cosmic structure and the ultimate fate of the universe. Two of the most enigmatic entities in our universe, supermassive black holes and dark matter, appear to be linked in ways that continue to puzzle and fascinate astronomers. On the surface, they seem entirely different. Black holes represent the ultimate concentration of normal matter, regions where gravity is so intense that nothing can escape, while dark matter is a mysterious substance that has never been directly observed, detected only through its gravitational effects on visible matter and light. Yet these cosmic phenomena influence each other in profound ways, their intertwined fates shaping the structure and evolution of galaxies throughout the cosmos. Dark matter makes up about 85% of all matter in the universe, yet it emits no light and interacts with normal matter primarily through gravity. Its existence was first inferred in the 1930s by astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving too quickly to be held together by the gravity of their visible matter alone. Subsequent observations, including the rotation curves of spiral galaxies and the gravitational lensing of distant light sources, have provided overwhelming evidence for dark matter's existence, though its fundamental nature remains one of the greatest unsolved mysteries in physics. The leading candidates for dark matter are exotic particles that interact very weakly with ordinary matter and electromagnetic radiation. These hypothetical particles, collectively known as weakly interacting massive particles, WIMPs, or more broadly as non-baryonic dark matter, would have been produced in the early universe and would now form vast halos that surround and permeate galaxies, extending far beyond the visible stellar component. Supermassive black holes, as we've explored throughout our journey, reside at the centers of nearly all large galaxies, including our own Milky Way. With masses ranging from millions to billions of times that of our Sun, these cosmic behemoths shape their surroundings through both their immense gravitational pull and, during active phases, their energetic outflows. Their formation and growth remain incompletely understood, with evidence suggesting a complex history involving both the accretion of gas and the mergers of smaller black holes following galaxy collisions. The relationship between these cosmic entities begins with the formation of the first structures in the early universe. After the Big Bang, the universe was nearly uniform, with only tiny fluctuations in density. Over time, gravity amplified these fluctuations, with regions of slightly higher density attracting more matter and becoming increasingly dense. Dark matter, being the dominant form of matter and interacting only through gravity, played the leading role in this process, forming the scaffolding upon which the visible universe would later be built. Computer simulations of cosmic evolution show that dark matter first condensed into small halos, which then merged hierarchically to form progressively larger structures. Gas followed the gravitational pull of these dark matter halos, flowing into their central regions where it could cool, condense, and eventually form the first stars and galaxies. This process naturally concentrated both dark and ordinary matter in the centers of these early cosmic structures. The exact role of dark matter in the formation of the first supermassive black holes remains uncertain, but several intriguing possibilities have been proposed. One theory suggests that the dense central regions of the earliest dark matter halos created gravitational potential wells that concentrated primordial gas to extraordinarily high densities, potentially leading to the direct collapse of massive gas clouds into black holes. These seeds could then have grown through accretion and mergers to become the supermassive black holes we observe today. Another possibility involves the formation of dense clusters of the first stars within dark matter halos. These population 3 stars, composed primarily of hydrogen and helium with minimal heavier elements, could have been much more massive than present-day stars. The most massive among them would have quickly exhausted their nuclear fuel and collapsed to form black holes, which could then have merged within these dense stellar environments to form larger intermediate mass black holes, the potential predecessors of supermassive black holes. Once formed, the relationship between supermassive black holes and dark matter becomes even more complex. The black hole, though initially containing only a tiny fraction of the galaxy's mass, resides at the precise center of the dark matter halo, where its gravitational influence can be significant. As the black hole grows by accreting gas and merging with other black holes, it increasingly influences the distribution of both ordinary matter and dark matter in its vicinity. Computer simulations suggest that as a black hole grows, it can alter the density profile of the surrounding dark matter halo, potentially creating a dark matter spike, a region of significantly enhanced dark matter density immediately surrounding the black hole. This process, known as adiabatic growth, occurs when the black hole grows slowly enough that the surrounding dark matter particles can adjust their orbits while conserving certain physical quantities, leading to a higher concentration of dark matter near the galactic center. However, other processes can counteract this concentration effect. If a galaxy experiences a major merger with another galaxy, the violent gravitational interactions can disrupt the central dark matter distribution, potentially erasing any dark matter spike. Similarly, if the central black hole binary undergoes a merger following a galaxy collision, the gravitational waves emitted during the final stages of this process can carry away energy and momentum, potentially giving the merged black hole a recoil kick that displaces it from the center of the dark matter halo, disrupting the central dark matter distribution. The interplay between supermassive black holes and dark matter also extends to larger scales through the process of structure formation. The energy released during active phases of black hole growth, in the form of radiation, winds, and jets, can heat and expel gas from the host galaxy and its surroundings. This feedback process not only regulates star formation, but also influences how much gas can cool and condense within the dark matter halo, affecting the overall distribution of visible matter relative to dark matter throughout the galaxy. In galaxy clusters, the largest gravitationally bound structures in the universe, the impact of central supermassive black holes extends even further. The jets emitted from active galactic nuclei in the central dominant galaxies of clusters can heat the intracluster medium, preventing it from cooling and flowing toward the center. This process, known as radio mode feedback, helps maintain the observed properties of galaxy clusters, including the relationship between dark matter, hot gas, and stars, which would otherwise be difficult to explain based on gravitational physics alone. One of the most intriguing questions regarding the relationship between supermassive black holes and dark matter is whether dark matter particles can be directly captured by black holes. Unlike ordinary matter, which can lose energy through electromagnetic interactions and fall into a black hole, dark matter particles interact very weakly with both ordinary matter and with each other. This makes it difficult for them to lose the energy and angular momentum necessary to be captured by a black hole. However, several mechanisms have been proposed through which dark matter might nevertheless be captured. One possibility involves the scattering of dark matter particles by stars or gas clouds near the black hole, which could cause some particles to lose energy and fall into lower orbits, eventually intersecting the event horizon. Another mechanism involves the gravitational capture of dark matter during the formation and growth of the black hole, particularly if the black hole forms in a region already dense with dark matter. If dark matter can indeed be captured by black holes, it raises fascinating possibilities. One is that black holes might serve as natural detectors of dark matter, with the accretion of these particles potentially producing observable effects. For instance, if dark matter particles annihilate with each other, as predicted by some theoretical models, the energy released inside or near a black hole might produce distinctive radiation signatures that could be detected with current or future telescopes. Another possibility is that the capture of dark matter by black holes could affect their properties and evolution. While the amount of dark matter captured would likely be small compared to the black hole's total mass, it could potentially influence the black hole's spin or charge, or affect the dynamics of material in the immediate vicinity of the event horizon. These effects, if they exist, would be extremely difficult to detect, but could in principle provide indirect evidence for the nature of dark matter. The distribution of dark matter around supermassive black holes also has implications for various proposed tests of general relativity. According to Einstein's theory, the spacetime around a black hole should be completely determined by just three parameters: mass, spin, and electric charge, which is typically negligible for astrophysical black holes. This prediction, known as the no-hair theorem, could in principle be tested by precise observations of stars or gas orbiting very close to a supermassive black hole. However, the presence of a dark matter spike or other dark matter structures near the black hole could complicate such tests by producing additional gravitational effects that might mimic deviations from general relativity. Disentangling these effects requires detailed modeling of both the black hole and its dark matter environment, highlighting the importance of understanding their relationship. Several observational approaches have been used to probe the connection between supermassive black holes and dark matter. One method involves measuring the relationship between black hole mass and the properties of the dark matter halo in which it resides. Studies have found correlations between black hole mass and the total mass of the host dark matter halo, suggesting a fundamental connection between their growth processes. Another approach examines the centers of dwarf galaxies, which are dominated by dark matter and often lack the violent events that could disrupt the central dark matter distribution. Some dwarf galaxies show evidence for central supermassive black holes, and the interaction between these black holes and the surrounding dark matter could produce distinctive density profiles that might be detected through careful observations of stellar motions. A particularly intriguing line of investigation involves searching for the products of dark matter annihilation from the regions around supermassive black holes. If dark matter particles can annihilate with each other, producing gamma rays or other high-energy radiation, the enhanced density near black holes could make these regions particularly bright sources of such radiation. Several gamma-ray telescopes, including the Fermi Gamma-Ray Space Telescope, have searched for these signals, though no definitive detection has been made. The relationship between supermassive black holes and dark matter also extends to their role in determining the overall structure of galaxies. The total mass and concentration of the dark matter halo influence the galaxy's size, rotation curve, and susceptibility to disturbances, while the central black hole can affect the distribution of stars and gas, particularly in the galactic bulge. Together, they help establish the observed scaling relations between galaxy properties, such as the relationship between stellar mass and rotation velocity, known as the Tully-Fisher relation. Looking toward the future, our understanding of the connection between supermassive black holes and dark matter will continue to evolve as new observations and theoretical developments emerge. Upcoming facilities like the James Webb Space Telescope, the Vera C. Rubin Observatory, and the Square Kilometre Array will provide unprecedented views of galaxies across cosmic time, potentially revealing new details about the coevolution of black holes and their dark matter environments. On the theoretical front, advances in computer simulations are allowing increasingly detailed modeling of the complex interplay between dark matter, gas dynamics, star formation, and black hole growth. These simulations, combined with analytical models, are helping to refine our understanding of how these processes interact over cosmic history and across the wide range of galactic environments observed in the universe. The ultimate nature of dark matter remains one of the greatest unsolved mysteries in modern physics, with implications that extend far beyond its relationship with black holes. Particle physics experiments on Earth are searching for direct evidence of dark matter particles, while astrophysical observations continue to map the distribution of dark matter throughout the cosmos. If and when dark matter's fundamental nature is discovered, it will likely reshape our understanding of its interaction with supermassive black holes and other cosmic structures. Similarly, our understanding of black holes continues to evolve, particularly regarding their formation in the early universe and their influence on galactic evolution. The direct imaging of black hole shadows, the detection of gravitational waves from black hole mergers, and the detailed mapping of matter distributions in galactic centers are providing new insights into these extraordinary objects and their cosmic role. The story of supermassive black holes and dark matter reflects a broader theme in modern astronomy: the interconnectedness of phenomena across vastly different scales, from the subatomic particles that may constitute dark matter to the supermassive black holes that can outweigh billions of suns, from the compact centers of galaxies to the vast cosmic web that spans billions of light years. The universe operates as an intricate system where each component influences and is influenced by the others. As we delve deeper into the cosmos, driven by human curiosity and enabled by increasingly powerful observational and computational tools, our understanding of these relationships will continue to deepen. The connection between supermassive black holes and dark matter, though still incompletely understood, represents one of the most fascinating chapters in this ongoing story of cosmic discovery. In many ways, both supermassive black holes and dark matter represent the frontiers of our knowledge, regions where our current understanding of physics is pushed to its limits, and perhaps beyond. By studying their interrelationship, we gain insights not only into these specific phenomena, but also into the fundamental laws that govern our universe, from the largest scales to the smallest, from the earliest moments after the Big Bang to the distant cosmic future. As we continue our exploration of supermassive black holes, we next turn to one of their most profound influences on the universe around them, the process known as feedback, through which these cosmic behemoths regulate the growth of their host galaxies and shape the evolution of cosmic structure. This complex interplay between black holes and their surroundings operating across vast distances and timescales, represents one of the most important discoveries in modern astrophysics and helps explain many of the observed properties of galaxies throughout the cosmos. Perhaps the most surprising discovery about supermassive black holes in recent decades is their outsized influence on the galaxies they inhabit. Despite typically accounting for less than 1% of a galaxy's total mass, these cosmic behemoths play a crucial role in regulating galactic growth and evolution through a process known as feedback. This remarkable phenomenon, through which the energy released by a feeding black hole affects gas across tens or even hundreds of thousands of light-years, represents one of nature's most important self-regulating mechanisms and helps explain many of the observed properties of galaxies throughout the cosmos. The concept of black hole feedback emerged as astronomers grappled with a fundamental puzzle in galaxy evolution. Why do galaxies look the way they do? Theoretical models that considered only gravity and standard gas physics predicted that most of the universe's baryonic matter, the ordinary matter made of protons, neutrons, and electrons, should have cooled and condensed to form stars within galaxies. Yet, observations show that only about 10% of this matter exists in the form of stars, with the remainder found in diffuse, hot gas within and between galaxies. Furthermore, the most massive galaxies in the universe, typically elliptical galaxies at the centers of galaxy clusters, appear to have stopped forming stars billions of years ago, despite being surrounded by vast reservoirs of gas that should, in principle, be cooling and forming new stars. Something must be preventing this gas from cooling efficiently, and that something appears to be the energy output from supermassive black holes. Black hole feedback operates through two main mechanisms, often called quasar mode and radio mode, each dominant under different conditions and with distinct effects on the surrounding galaxy. Understanding these processes requires first appreciating the extraordinary amount of energy released when matter falls into a black hole. When gas accretes onto a supermassive black hole, it typically forms a rotating disk, with friction and magnetic fields causing the gas to heat to millions of degrees. Before crossing the event horizon, this superheated material can release up to 10% of its rest mass energy, the energy equivalent of its mass according to Einstein's famous equation E equals mc squared. This efficiency dwarfs that of nuclear fusion in stars, which converts less than 1% of mass to energy, making black hole accretion the most efficient energy-producing process known in the universe. During periods of intense accretion, such as those observed in quasars and active galactic nuclei, this energy is released primarily in the form of electromagnetic radiation, spanning the spectrum from radio waves to gamma rays, along with powerful winds of gas driven outward by radiation pressure. This quasar mode feedback is particularly important in gas-rich galaxies, where the black hole is feeding rapidly on abundant fuel. The radiation and winds from an active galactic nucleus can interact with surrounding gas in several ways. The intense radiation can heat the gas directly, increasing its pressure and preventing it from collapsing under gravity to form stars. It can also destroy molecules like hydrogen that would otherwise cool the gas efficiently, further suppressing star formation. The radiation pressure can push gas outward from the galactic center, potentially driving vast outflows that can expel material entirely from the galaxy. These quasar-driven outflows can be spectacular, with velocities sometimes exceeding 1,000 kilometers per second and mass flow rates of hundreds of solar masses per year. Such powerful outflows can sweep through a galaxy like cosmic tsunamis, disrupting gas clouds that might otherwise form stars, and even ejecting significant fractions of the galaxy's gas reservoir into intergalactic space. Observations of these outflows, particularly in infrared luminous galaxies and quasars, reveal their profound impact on their host galaxies. Spectroscopic studies show gas moving at thousands of kilometers per second, far exceeding the escape velocity of typical galaxies. Spatially resolved observations demonstrate that these outflows can extend for tens of thousands of light-years, affecting the entire galaxy and not just its nuclear regions. The energy required to drive such powerful outflows comes ultimately from the gravitational potential energy of matter falling into the black hole. converted to radiation and kinetic energy with remarkable efficiency. A supermassive black hole accreting at close to its theoretical maximum rate, the Eddington limit, can release energy equivalent to the explosion of billions of supernovae each year, more than enough to unbind much of the gas from a massive galaxy. This quasar-mode feedback appears to be particularly important during certain phases of galaxy evolution, especially following the merger of two gas-rich galaxies. Such mergers can drive large amounts of gas toward the galactic center, triggering both intense star formation and rapid black hole growth. The resulting quasar activity can then expel much of the remaining gas, effectively shutting down both star formation and further black hole growth in a self-limiting process. This scenario helps explain the observed correlation between black hole mass and galaxy properties, such as the mass and velocity dispersion of stars in the galactic bulge. If black hole growth and star formation proceed together until feedback from the black hole expels the remaining gas, we would expect just such a relationship between final black hole mass and bulge properties, as observed. The second major form of black hole feedback, known as radio mode or maintenance mode, operates differently and dominates in different environments. This mode is typically associated with black holes that are accreting at much lower rates than those powering bright quasars, often in massive elliptical galaxies or at the centers of galaxy clusters where gas densities are lower. In these systems, the black hole's energy output is dominated not by radiation, but by kinetic energy in the form of relativistic jets, narrow beams of plasma ejected along the black hole's rotation axis at speeds approaching that of light. These jets, visible primarily at radio wavelengths, hence the name radio mode, can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of the host galaxy. As these powerful jets propagate through the hot gas surrounding the galaxy, they create shock waves and inflate enormous bubbles or cavities. These structures are particularly evident in X-ray observations of galaxy clusters, where the hot intracluster medium, with temperatures of millions of degrees, emits X-rays that are blocked or diminished in regions where the jets have pushed the gas aside. The energy transferred from the jets to the surrounding medium primarily takes the form of mechanical work, the energy required to inflate these cavities against the pressure of the surrounding gas. While less spectacular than the radiation-driven outflows of quasar-mode feedback, this mechanical heating can be remarkably effective at preventing the hot gas in and around massive galaxies from cooling and flowing inward to form stars. This process creates a self-regulating cycle. As hot gas begins to cool and flow toward the galactic center, some of it accretes onto the central black hole, triggering jet activity. The jets then heat the surrounding gas, preventing further cooling and inflow. When the gas stops flowing inward, the black hole's activity diminishes, allowing the cycle to begin again. This thermostat-like regulation helps explain why the centers of galaxy clusters maintain nearly constant temperatures over billions of years, rather than cooling and forming stars as simple physical models would predict. The effectiveness of radio mode feedback stems partly from its persistence. While quasar activity typically lasts for only millions to tens of millions of years, limited by the available gas supply or the expulsion of gas by radiation pressure, jets can operate at lower power for hundreds of millions or even billions of years, providing a steady source of heating to counteract the natural cooling of gas in and around massive galaxies. The bubbles and cavities created by radio jets also serve as fossil records of past black hole activity, allowing astronomers to estimate the total energy injected by the central black hole over time. By measuring the size and pressure of these cavities, researchers can calculate the energy required to create them, typically finding values equivalent to millions or billions of supernovae, enormous but consistent with the expected energy output from accreting supermassive black holes. Remarkably, the two modes of black hole feedback appear to dominate at different cosmic epochs and in different environments, creating a comprehensive regulatory system that has operated throughout much of the universe's history. Quasar mode feedback was particularly important during the peak of cosmic star formation about 10 billion years ago, when gas was abundant and galaxy mergers frequent. This intense period, sometimes called cosmic noon, saw the most rapid growth of both black holes and galaxy bulges, with feedback eventually limiting their sizes and establishing the observed correlations between them. Radio mode feedback, in contrast, has become increasingly important in the more recent universe, particularly in massive galaxies and galaxy clusters where gas densities are lower and cooling processes less efficient. This mode helps maintain the red and dead state of massive elliptical galaxies, preventing the hot gas surrounding them from cooling and forming new stars that would change their appearance from red to blue. The transition between these modes over cosmic time helps explain the observed evolution of the galaxy population from the profusion of gas-rich, star-forming galaxies in the early universe to the mix of spirals and ellipticals we observe today. The most massive galaxies, which experienced the most intense quasar feedback early in their history, followed by long-term radio mode feedback, have largely ceased forming stars and appear as red ellipticals. Less massive galaxies, where feedback was less disruptive, have often retained enough gas to continue forming stars, appearing as blue spirals like our own Milky Way. The specific mechanisms through which black hole energy couples to surrounding gas remain active areas of research. In quasar mode, radiation pressure on dust grains appears to be particularly important, as dust can absorb and scatter radiation across a wide range of wavelengths, efficiently transferring momentum from the radiation field to the gas. Additionally, the intense radiation can heat gas to temperatures of tens of thousands of degrees, creating high-pressure regions that expand and drive outflows. In radio mode, several heating mechanisms operate simultaneously. The jets create shock waves as they propagate through the surrounding medium, directly heating the gas they encounter. The inflation of bubbles performs mechanical work against the surrounding pressure, effectively transforming the kinetic energy of the jets into thermal energy of the gas. Additionally, the rising bubbles can generate turbulence and waves that distribute energy throughout the surrounding medium, heating it more uniformly than direct interaction with the jets alone would allow. The effectiveness of these processes depends on the properties of both the black hole and its surroundings. More massive black holes can release more energy, but the coupling of this energy to the surrounding gas depends on factors such as gas density, temperature, and composition. In very dense environments, radiation may be trapped or absorbed close to the black hole, reducing its impact on larger scales. Similarly, jets may be disrupted or confined in dense environments, limiting their reach but potentially increasing their local heating efficiency. Observations across the electromagnetic spectrum have revealed the diversity and complexity of black hole feedback in action. Optical and ultraviolet spectroscopy can detect the signatures of fast-moving gas in quasar-driven outflows. Infrared observations reveal the impact of these outflows on dust and molecular gas, the raw material for star formation. X-ray studies show the hot gas that fills galaxy clusters and bears the imprint of jet activity in the form of bubbles and shock fronts. Radio observations trace the jets themselves, revealing their structure, propagation, and interaction with the surrounding medium. These multi-wavelength data, combined with increasingly sophisticated computer simulations, are helping astronomers understand the physics of black hole feedback in detail. Modern simulations can now model the gas dynamics, radiation transport, magnetic fields, and relativistic effects necessary to capture the full complexity of these processes, from the immediate vicinity of the black hole to scales spanning entire galaxy clusters. One of the most striking results from these simulations is the demonstration that without black hole feedback, our universe would look very different. Models that include only gravity, gas dynamics, and stellar processes, like supernova explosions, consistently predict galaxies that are too massive, too blue, and too concentrated compared to observations. Including black hole feedback brings these models into much better agreement with the observed properties of galaxies, suggesting that this process is indeed fundamental to understanding cosmic evolution. The importance of black hole feedback extends beyond individual galaxies to the largest structures in the universe. In galaxy clusters, the hot intra-cluster medium contains more baryonic mass than all the stars in all the cluster galaxies combined. Without the heating provided by central supermassive black holes, much of this gas would cool and form stars, dramatically altering the appearance and properties of these massive systems. Black hole feedback thus helps establish and maintain the observed distribution of matter on scales of millions of light years, influencing the basic architecture of the cosmic web. The relationship between black hole feedback and star formation represents one of the most important aspects of this process. While feedback often suppresses star formation by heating or expelling gas, it can sometimes enhance it by compressing gas clouds or triggering instabilities that lead to collapse and star formation. This dual nature, both creative and destructive, makes the net impact of feedback complex and dependent on local conditions. In some systems, particularly gas-rich galaxies with moderate black hole activity, observations reveal regions of enhanced star formation along the edges of outflows or jets, where the pressure from these features compresses the gas to densities high enough to trigger collapse. These positive feedback effects, while typically localized and temporary, demonstrate the complex interplay between black hole energy and the surrounding interstellar medium. More commonly, however, the net effect of black hole feedback on star formation is negative, particularly in massive galaxies and over long timescales. Statistical studies of galaxy populations show that the most massive galaxies, which host the largest black holes, have the lowest specific star formation rates, star formation per unit stellar mass, consistent with more effective feedback. Similarly, galaxies with active central black holes often show reduced star formation compared to similar galaxies with inactive nuclei, though this relationship can be complex due to the different timescales involved and the varying effectiveness of feedback in different environments. The balance between positive and negative feedback, between heating and cooling, between inflow and outflow, creates a regulatory system that has profoundly shaped the evolution of galaxies throughout cosmic history. Without this regulation, galaxies would have converted much more of their gas into stars, resulting in a universe with fewer, more massive galaxies and less diffuse gas between them. The observed galaxy population, with its diverse mix of star-forming spirals and quiescent ellipticals, its wide range of masses and colors, and its complex interplay between different components, bears the clear imprint of black hole feedback's profound influence. Looking toward the future, our understanding of black hole feedback will continue to evolve as new observations and simulations provide deeper insights into these complex processes. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spatial resolution, will reveal the impact of feedback on gas and dust in distant galaxies, tracing the co-evolution of black holes and their hosts during the peak of cosmic activity. Advanced radio facilities like the Square Kilometre Array will provide detailed views of jets and their environments, revealing how energy propagates from black holes to larger scales. On the theoretical front, increasingly sophisticated simulations, incorporating more realistic physics and spanning wider ranges of scales, will help clarify the relative importance of different feedback mechanisms in various environments and at different cosmic epochs. These simulations, combined with analytical models, will refine our understanding of how black holes regulate galaxy growth and establish the observed correlations between black hole and galaxy properties. The story of black hole feedback represents one of the most remarkable discoveries in modern astrophysics. The recognition that some of the smallest objects in the universe, when viewed in terms of physical size, exert profound influence over some of the largest structures. From event horizons measuring just light hours across to effects spanning millions of light years, the energy flowing from supermassive black holes helps shape the visible universe into the form we observe today. This cosmic regulatory system, operating across billions of years of cosmic history, demonstrates the interconnectedness of phenomena across vastly different scales. From the quantum effects that ultimately govern accretion processes near the event horizon to the large-scale structure of the cosmic web. In many ways, Black hole feedback epitomizes the holistic nature of modern astrophysics, where understanding any component of the universe requires appreciating its relationships with all others. As we continue our exploration of supermassive black holes, we next turn from their effects on their surroundings to a more speculative but equally fascinating question. What would happen if one were to venture too close to these cosmic behemoths? What would a human observer experience as they approached the event horizon, the boundary beyond which nothing, not even light, can escape? This journey to the edge of the knowable universe reveals some of the most exotic predictions of Einstein's theory of general relativity and challenges our intuitive understanding of space, time, and the nature of reality itself. Having explored the cosmic impact of supermassive black holes, from their formation to their profound influence on galactic evolution, let us now embark on a more intimate and speculative journey, a theoretical voyage to the very edge of one of these cosmic behemoths. What would it be like to approach a supermassive black hole? What strange relativistic effects would manifest as you neared the event horizon, the boundary beyond which nothing, not even light, can escape? While such a journey remains firmly in the realm of thought experiments, the nearest supermassive black hole, Sagittarius A star at the center of our galaxy, lies some 26,000 light-years from Earth. The physics of general relativity allows us to predict with remarkable precision what such an intrepid traveler would experience. Our journey begins far from the black hole, where space-time is nearly flat and the laws of physics operate much as they do on Earth. From this distance, a supermassive black hole would be invisible against the backdrop of stars, betraying its presence only through its gravitational effects on nearby objects. If the black hole is actively feeding, we might observe the glow of its accretion disk, the spiraling matter about to be consumed, or perhaps jets of energetic particles launched from its poles. But the black hole itself emits no light, appearing instead as a dark silhouette against any light sources behind it. As we approach this cosmic giant, the first noticeable effect would be gravitational lensing, the bending of light paths due to the curvature of space-time around the black hole. Stars and galaxies behind the black hole would appear displaced from their true positions, with objects directly behind it appearing as rings or partial arcs around the black hole. This effect, first confirmed during a solar eclipse in 1919 as one of the triumphant predictions of Einstein's general relativity, becomes drastically more pronounced near a black hole's immense gravity. The visual distortion increases as we draw nearer. Stars that are actually behind the black hole may appear to be on either side of it, their light bent around the massive object. Some stars might appear in multiple locations simultaneously as different light paths from the same source curve around the black hole at different angles. The entire sky would seem to warp and flow around the dark central region, creating a disorienting visual landscape unlike anything experienced on Earth. For a supermassive black hole with millions or billions of solar masses, these effects unfold over vast distances, unlike their stellar mass cousins, where significant gravitational effects become apparent only when extremely close. Supermassive black holes distort space-time over regions larger than our entire solar system. This extended influence has profound implications for our journey, as it means the gravitational gradient, the rate at which the gravitational force increases as we get closer, is actually much gentler for supermassive black holes than for smaller ones. This relatively gentle gradient means that a human approaching a supermassive black hole would not immediately be torn apart by tidal forces. The difference in gravitational pull between the side of an object closest to the black hole and the side farthest away. For a stellar mass black hole, these tidal forces would become lethal well before reaching the event horizon, stretching and compressing any physical object in a process colorfully termed spaghettification. But for a black hole with millions or billions of solar masses, one could theoretically cross the event horizon without experiencing fatal tidal forces. As our journey continues inward, we begin to notice the effects of time dilation, one of the most profound and counterintuitive consequences of general relativity. Time passes more slowly in stronger gravitational fields, a phenomenon called gravitational time dilation. Near a black hole, this effect becomes extreme. If we were to hover at a fixed distance from the black hole, requiring enormous thrust to counteract its gravitational pull, we would observe that our clocks run slower than identical clocks located farther away. From the perspective of distant observers watching our journey, our time would appear to slow dramatically as we approach the black hole. If we were sending regular signals back to Earth, those monitoring our progress would receive these signals with increasingly longer intervals between them. As we near the event horizon, signals would be separated by gaps that grow exponentially longer. From their perspective, it would take an infinite amount of time for us to reach the event horizon itself, as if our journey were being stretched out to eternity. However, from our own perspective as the travelers, time would continue to flow normally. We would not sense our time slowing down. Our heartbeats and thoughts would seem unchanged to us. The discrepancy between our experience and that of distant observers represents one of the most profound aspects of relativity, the relativity of simultaneity. The recognition that observers in different reference frames no longer agree on whether events occur simultaneously. Accompanying this time dilation is a corresponding effect on light known as gravitational redshift. As photons climb out of a gravitational well, they lose energy, shifting to longer wavelengths. For visible light, this means shifting toward the red end of the spectrum, hence the term redshift. For signals sent from near a black hole to distant observers, this redshift becomes extreme, with the wavelength stretching by larger and larger factors as the source approaches the event horizon. From our perspective as travelers, incoming light from distant sources would be blue-shifted, compressed to shorter wavelengths, as it falls into the gravitational well with us. Looking outward, we would see the universe accelerated, with events that might take years or centuries in the outside world appearing to unfold much more rapidly. Stars would age visibly, galaxies would rotate perceptibly, and the cosmic expansion would accelerate before our eyes. A fast-forward glimpse of cosmic evolution. This changing relationship with the outside universe represents one of the most poignant aspects of our journey. As we approach the event horizon, the universe we leave behind begins to recede, not just in space, but in time. The signals we send take longer and longer to reach distant observers, while information from the outside universe reaches us at an accelerated rate. We become temporarily disconnected from our point of origin, experiencing what might be called relativistic isolation. Another dramatic effect emerges as we draw closer, the apparent visual distortion of the black hole itself. From a distance, the black hole appears as a dark circle against the background of stars, but as we approach, this circle expands disproportionately, growing to fill more and more of our field of view. This is not merely because we're getting closer, but because of the extreme bending of light paths in the severely curved spacetime near the black hole. At a certain point, the apparent size of the black hole reaches a maximum, a visual effect created when light rays can complete half orbits around the black hole before reaching our eyes. Beyond this point, we begin to see light from behind us that has orbited the black hole completely. If we had a perfect omnidirectional view, we could theoretically see the back of our own spacecraft, or even the back of our own head, as light completes full orbits around the black hole before entering our eyes. These visual distortions reach their peak as we approach the photon sphere, a region where light can orbit the black hole in perfect circles. For a non-rotating black hole, this occurs at 1.5 times the Schwarzschild radius, the radius of the event horizon. At this distance, a photon traveling perpendicular to our radial direction can orbit the black hole indefinitely, neither falling in nor escaping to infinity. If we could somehow hover at this precise location and look in a direction tangent to this sphere, we would theoretically see the back of our own head as light completes a full circle around the black hole. For our supermassive black hole, the photon sphere might be millions or billions of kilometers in radius, large enough to enclose entire stellar systems. Yet despite this vast size, the extreme physics at work here bears little resemblance to our everyday experience. The very concept of seeing becomes almost meaningless as light rays curve and spiral in complex paths, creating visual paradoxes that challenge our intuitive understanding of space and perspective. As we continue our inward journey, we eventually approach the event horizon itself, the point of no return. The event horizon is not a physical surface, but a boundary in space-time. There is no wall to crash into, no barrier that repels incoming matter. Rather, it represents a region where space-time is so severely curved that all future paths lead inexorably inward. Once crossed, there is no trajectory, not even for light traveling at the universe's ultimate speed limit, that can reach the outside universe again. What would we experience as we cross this boundary? From our perspective as travelers, surprisingly little. For a supermassive black hole, where tidal forces at the horizon are relatively mild, we would not feel any dramatic physical sensation marking our passage across this cosmic point of no return. Our instruments would continue to function, our bodies would remain intact, and we could still look outward and see the universe behind us. The horizon crossing itself, for a freely falling observer, is not marked by any locally detectable physical effect. This anticlimactic crossing highlights one of the central principles of general relativity, the equivalence principle. In a freely falling reference frame, the effects of gravity are equivalent to acceleration. Just as a person in a closed elevator cannot tell whether they are accelerating upward or being pulled down by gravity, a traveler crossing an event horizon in free fall experiences no special local effects that would signal their passage across this boundary. However, our relationship with the outside universe changes irrevocably at this moment. As we cross the horizon, the light cone, the set of possible paths that light rays can take from our position, tilts so severely that all future directed paths point inward. No signal we send, no matter how powerful, can ever reach the universe outside the horizon. We have entered a region from which there is no escape, not due to insufficient thrust or energy, but because the very geometry of space-time permits only one direction of travel, toward the center of the black hole. For a supermassive black hole, the distance from the event horizon to the central singularity could be millions or billions of kilometers. This gives us a significant amount of proper time as measured by our own clocks, after crossing the horizon before encountering extreme conditions near the center. Depending on the black hole's mass, this remaining journey might last minutes, hours, or even days from our perspective. During this post-horizon phase of our journey, we could still see the external universe behind us. Light from stars and galaxies would continue to reach us, though increasingly blue-shifted and concentrated in a shrinking patch of sky directly opposite our direction of travel. Ahead of us, however, there would be only darkness. No light can reach us from regions deeper inside the black hole. As all light, there is also directed inward. As we continue our inevitable plunge toward the center, the relatively gentle conditions near the event horizon gradually give way to more extreme physics. Tidal forces, the differential gravitational pull that stretches objects vertically while compressing them horizontally, grow stronger. For a supermassive black hole, these forces would remain survivable for a considerable distance inside the horizon, but eventually they would reach levels that no physical material, including human bodies or spacecraft, could withstand. This is where the journey becomes truly destructive. Our theoretical traveler would be stretched vertically and compressed horizontally with ever-increasing force. Every physical object, regardless of its composition or strength, eventually reaches its breaking point. At the atomic level, the tidal forces would eventually overcome the electromagnetic forces that hold matter together, reducing even the most sophisticated spacecraft and its occupants to a stream of elementary particles, all following their inevitable path toward the central singularity. The nature of this singularity, the central point where matter is crushed to infinite density, and space-time curvature becomes infinite, represents one of the greatest unsolved problems in theoretical physics. According to classical general relativity, all the matter that falls into a black hole is ultimately crushed into this mathematical point of zero volume and infinite density. However, most physicists believe that this prediction represents a failure of the theory rather than a physical reality, as quantum effects should become important before reaching such extreme conditions. A complete theory of quantum gravity, which would unite general relativity with quantum mechanics, might replace the singularity with something else, perhaps a tiny region of extremely curved but non-infinite spacetime, or a gateway to another region of space, or even another universe. This possibility, sometimes associated with speculative concepts like wormholes or white holes, remains firmly in the realm of theoretical physics, with no observational evidence to support or refute these ideas. For our purposes, we can say with certainty that no physical observer would survive to report on the nature of the singularity. The extreme tidal forces within the black hole would destroy any organized matter well before reaching the central region, terminating our theoretical journey in a very physical way. But what about information? If we sent detailed records of our journey toward the outside world before crossing the event horizon, what would happen to this information? This question touches on one of the most profound puzzles in modern physics, the black hole information paradox. Quantum mechanics suggests that information cannot be destroyed, yet black holes seem to erase the information contained in anything that falls into them, reducing all matter, regardless of its initial state, to the same final state, characterized by just three parameters: mass, charge, and angular momentum. Theoretical developments in recent decades, particularly in string theory and the concept of holography, suggest that information might not be truly lost. Instead, it might be encoded on the event horizon itself, preserved in a scrambled form that could, in principle, be reconstructed. Alternatively, it might be released gradually as the black hole evaporates through Hawking radiation, a quantum process by which black holes are expected to lose mass over time, albeit at an extraordinarily slow rate for supermassive black holes. The resolution of this paradox remains an active area of research at the frontier of theoretical physics, where general relativity, quantum mechanics, and thermodynamics intersect. The answers may provide crucial insights not just into the nature of black holes, but into the fundamental structure of spacetime and information at the most basic level. Returning to our more experiential journey, it's worth considering some additional effects that would manifest for a rotating black hole, a more realistic scenario, as most supermassive black holes are expected to have significant angular momentum, unlike the spherically symmetric Schwarzschild black holes we've primarily discussed. Rotating, Kerr, black holes have more complex geometry, with different event horizon shapes and additional regions like the ergosphere, where spacetime itself is dragged around the black hole. In the ergosphere, a region outside the event horizon where spacetime is dragged around the black hole at speeds exceeding the speed of light, strange effects become possible. An object in this region could, in principle, extract energy from the black hole's rotation through a process known as the Penrose process, effectively converting some of the black hole's rotational energy into other forms. This region also allows for more complex orbits, including those that could, in principle, enable escape from deep within the black hole's gravitational well. For an observer falling into a rotating black hole, the path toward the singularity becomes more complex. Rather than a single point, the singularity in a Kerr black hole takes the form of a ring, and certain trajectories might avoid hitting this ring singularity directly. Some theoretical solutions to Einstein's equations even suggest the possibility of paths that lead not to destruction, but to other regions of spacetime, perhaps even other universes. However, most physicists consider these solutions unlikely to represent physical reality, as they rely on perfectly ideal conditions and ignore quantum effects that would likely become important in these extreme regimes. Our theoretical journey to a supermassive black hole reveals not just the extraordinary physics of these cosmic objects, but also the profound implications of Einstein's general relativity for our understanding of space, time, and reality itself. The warping of spacetime near black holes creates effects that defy our intuitive understanding of the universe, from the slowing of time to to the bending of light paths, from the inevitability of the central singularity to the paradoxes surrounding information and entropy. While human travelers are unlikely to ever directly experience these phenomena, the nearest supermassive black hole is far beyond our current technological reach, and the journey would be one way even if we could get there. Our theoretical understanding of these effects helps us interpret astronomical observations and develop a deeper comprehension of the fundamental laws of physics. The extreme conditions near black holes provide a natural laboratory for testing theories at the limits of our knowledge, potentially pointing the way toward a more complete understanding of the universe at its most fundamental level. As we conclude our theoretical journey to the event horizon and beyond, we're left with a profound appreciation for both the power of human intellect to understand such exotic phenomena from a safe distance, and the humbling recognition of how strange and wonderful the universe becomes when examined at its extremes. These cosmic behemoths, with their ability to warp the very fabric of reality, continue to fascinate astronomers, physicists, and the general public alike, representing one of the most extraordinary predictions of modern physics that has, against all intuitive expectations, proven to be an essential component of our cosmic reality. Having ventured to the very edge of current physical understanding in our theoretical journey to the event horizon, we now turn our attention to the future, how our knowledge of supermassive black holes will continue to evolve as new observational facilities and theoretical approaches come online. The study of these cosmic extremes represents one of the most dynamic and rapidly advancing fields in modern astrophysics, with new discoveries continually reshaping our understanding of these extraordinary objects and their role in the cosmos. As we gaze into the depths of space, our understanding of supermassive black holes stands on the precipice of a revolution. The discoveries we've made so far represent merely the opening chapter in humanity's ongoing relationship with these cosmic leviathans. The coming decades promise to transform our understanding of these enigmatic objects that have captivated our imagination since they were first theorized. The Event Horizon Telescope, which captured the world's attention with its groundbreaking first image of a black hole's shadow in 2019, is far from finished with its cosmic photography session. This global network of synchronized radio telescopes, acting as a virtual Earth-sized observatory, is being continuously upgraded and expanded. Scientists are already planning observations of Sagittarius A star, the supermassive black hole lurking at the center of our own Milky Way galaxy. Unlike Messier 87's behemoth, our galactic center's black hole is far less active, presenting unique observational challenges, but offering insights into the more common dormant state of these cosmic giants. Future upgrades to the Event Horizon Telescope will include additional telescopes at strategic locations around the globe and even in space. These enhancements will sharpen our view, potentially revealing not just the shadow of the event horizon, but the complex structures of the surrounding accretion disks and relativistic jets in unprecedented detail. Researchers hope to capture dynamic processes unfolding in real time, creating not just images, but movies of matter circling the drain of eternity. But visual observations represent just one avenue of exploration. Perhaps even more exciting is the rapidly maturing field of gravitational wave astronomy, which has opened an entirely new sensory channel to the universe. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, and its European counterpart Virgo have already detected the space-time ripples from dozens of black hole mergers. However, these observatories are primarily sensitive to the mergers of stellar mass black holes, the smaller cousins of the supermassive variety. To detect the gravitational waves from supermassive black hole mergers, we need even more sophisticated instruments. Enter the Laser Interferometer Space Antenna, or LISA, a planned space-based gravitational wave observatory consisting of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers. By placing the detectors in space, scientists can avoid the seismic noise that limits ground-based observatories and create an instrument sensitive to the lower frequency gravitational waves produced when galaxies and their central black holes collide. When LISA launches, anticipated in the mid-2030s, it will allow us to witness the final dance of merging supermassive black holes across the observable universe. These observations will not only confirm or refute our current theories of black hole growth, but also provide precise measurements of black hole spins and masses, testing Einstein's general relativity in the most extreme gravitational environments known. Complementing these efforts, next-generation X-ray observatories like the Advanced Telescope for High-Energy Astrophysics, or Athena, and the Lynx X-ray Observatory will peer into the heart of active galactic nuclei with unprecedented sensitivity and spectral resolution. These observatories will allow scientists to study the hot, turbulent environment immediately surrounding supermassive black holes, measuring the temperature, density, and chemical composition of matter just before it crosses the event horizon. By analyzing how X-rays are reflected and distorted by the intense gravitational field near the event horizon, these observatories could potentially map the spacetime around supermassive black holes with exquisite precision. Such measurements might even reveal deviations from the predictions of general relativity, hinting at new physics beyond our current understanding. The James Webb Space Telescope, with its unparalleled infrared sensitivity, will peer back through cosmic time to witness the formation of the earliest galaxies and their nascent central black holes. By studying these cosmic seeds from the universe's infancy, we may finally resolve the chicken and egg problem of whether supermassive black holes helped form galaxies, or whether galaxies gave birth to these cosmic monsters. Webb's observations will be complemented by ground-based behemoths like the extremely large telescope, with its colossal 39-meter primary mirror. This instrument will achieve such high resolution that it could potentially track individual stars as they orbit the supermassive black hole at our galaxy's center, tracing out the invisible gravitational well with unprecedented precision. But perhaps the most tantalizing possibility lies in the combination of these different observational approaches, what astronomers call multi-messenger astronomy. By simultaneously observing black holes across the electromagnetic spectrum and through gravitational waves, we can build a comprehensive picture impossible through any single method. Imagine witnessing a supermassive black hole merger first through the gravitational waves detected by LISA, then watching as X-ray and radio telescopes capture the electromagnetic aftermath of this cosmic collision. Such coordinated observations could reveal how these mergers reshape their host galaxies and trigger bursts of star formation or quasar activity. As computational power continues to grow exponentially, so too does our ability to simulate black hole physics with increasing sophistication. The next generation of supercomputers will enable simulations that track the formation and evolution of supermassive black holes from the cosmic dawn to the present day, accounting for the complex interplay between black holes, their host galaxies, and the larger cosmic web. These simulations, combined with machine learning algorithms trained on vast astronomical datasets, may identify subtle patterns and correlations invisible to human researchers. Artificial intelligence could potentially discover new categories of black hole phenomena or unexpected relationships between black hole properties and their cosmic environments. Theorists, meanwhile, continue to grapple with the profound paradoxes that black holes present to our understanding of fundamental physics. The information paradox, the apparent destruction of information when matter falls into a black hole, strikes at the heart of quantum mechanics, which holds that information can never be truly destroyed. Recent theoretical work suggests that information might be preserved in subtle quantum correlations at the event horizon or encoded in the gravitational field itself. The quest to reconcile quantum mechanics with general relativity, our two most successful but fundamentally incompatible physical theories, may find its most crucial testing ground in the extreme environment of black holes. String theory, loop quantum gravity, and other approaches to quantum gravity make different predictions about what happens at the singularity at a black hole's center, a point where space-time curvature becomes infinite and our current physical theories break down completely. While directly observing a singularity remains impossible, Hidden as it is behind the event horizon, certain quantum gravity effects might manifest in observable ways, particularly in the gravitational waves emitted during black hole mergers. The residual ring-down after a merger, as the newly formed black hole settles into a stable state, could contain subtle signatures of quantum gravity, providing tantalizing glimpses of physics beyond the standard model. Some theorists have even proposed more exotic possibilities, that supermassive black holes might serve as bridges to other universes or distant regions of our own universe. While such wormhole scenarios remain firmly in the realm of speculation, they highlight the profound role that black holes play in our exploration of the universe's deepest mysteries. As we push the boundaries of what we can observe and calculate, we might discover entirely new phenomena associated with supermassive black holes. Perhaps we'll find evidence of primordial black holes, formed not from collapsed stars, but from density fluctuations in the very early universe, which could explain some of the missing mass attributed to dark matter. Or we might detect the subtle effects of quantum vacuum fluctuations near event horizons, manifesting as a faint glow of Hawking radiation. The international nature of black hole research reflects an important truth. Understanding these cosmic behemoths requires a global effort. Scientists from dozens of countries collaborate on projects like the Event Horizon Telescope, sharing resources, expertise, and observing time in pursuit of common goals. In an age of increasing geopolitical tensions, such collaborations serve as powerful reminders of humanity's shared curiosity about our universe. Young researchers entering the field today stand on the shoulders of giants like Stephen Hawking, Kip Thorne, and Roger Penrose, whose theoretical insights laid the groundwork for our current understanding. These new scientists bring fresh perspectives and innovative approaches, harnessing technologies that their predecessors could only dream of. The democratization of astronomical data, with many major observatories making their observations publicly available, has enabled researchers from around the world to contribute to our understanding of black holes, regardless of their access to expensive equipment. Education and public outreach form another crucial frontier in black hole research. The iconic image of Messier 87's supermassive black hole captured the public imagination in a way few scientific discoveries have, appearing on magazine covers, t-shirts, and social media feeds worldwide. This public fascination creates opportunities to engage people of all ages with the wonders of astronomy and the importance of basic research. Museums and planetariums have developed immersive experiences that allow visitors to visualize the warping of space-time around black holes or virtually journey to the event horizon. Online resources provide everyone, from schoolchildren to retirees, with access to real astronomical data and tools to explore it. This broad engagement ensures that future generations will continue to be inspired by these cosmic mysteries, following their curiosity toward careers in science, technology, engineering, and mathematics. The economic implications of black hole research extend beyond pure scientific knowledge. Technologies developed for astronomical observations often find applications in medicine, industry, and consumer products. The image processing algorithms created for the Event Horizon Telescope, for instance, could improve medical imaging techniques, while the precise timing systems required for coordinated observations might enhance global navigation and communication networks. As private companies increasingly venture into space, some visionaries have proposed ambitious projects that might one day revolutionize our study of black holes. Gravitational lenses, the bending of light around massive objects, could potentially be used to create a telescope of unprecedented power. By positioning a spacecraft at the focal point where our sun focuses light from a distant black hole, we could achieve magnification factors of millions or even billions, revealing details currently unimaginable. Such projects, while still theoretical, highlight the limitless possibilities that await us as we continue to push the boundaries of technology and imagination. From quantum computers simulating black hole interiors to swarms of coordinated nanosatellites forming virtual telescopes larger than the Earth, the future methods of studying these cosmic enigmas may be as mind-bending as the objects themselves. The search for extraterrestrial intelligence, or SETI, intersects with black hole research in fascinating ways. Some have speculated that advanced civilizations might harness the energy of supermassive black holes, either by extracting rotational energy through elaborate mechanisms or by collecting the intense radiation from matter falling into the black hole. Such black hole engines would represent the pinnacle of technological achievement, visible across vast cosmic distances. SETI researchers have proposed scanning the vicinity of distant supermassive black holes for unusual energy signatures that might indicate such technological interventions. In the far future, humanity might even develop the capability to study black holes up close, sending specialized probes to orbit just outside the event horizon of these cosmic monsters. Such missions would require technologies far beyond our current capabilities, propulsion systems approaching the speed of light, materials that can withstand extreme gravitational forces, and communication methods that can overcome the severe time dilation effects near massive black holes. The pursuit of knowledge about supermassive black holes represents one of humanity's grandest intellectual adventures. It challenges us to think on scales from the subatomic to the cosmic, to develop technologies that stretch the limits of what's possible, and to collaborate across borders and disciplines. As we gaze into these darkest objects in the universe, we illuminate not just the cosmos, but ourselves, our capacity for wonder, our ingenuity in the face of challenges, and our endless quest to understand the universe and our place within it. As we continue this journey, we must remember that the greatest discoveries often come from unexpected directions. The history of astronomy is filled with serendipitous findings that revolutionized our understanding, from pulsars discovered by Jocelyn Bell Burnell, as unusual scruff in radio telescope data, to the accelerating expansion of the universe revealed through careful observations of distant supernovae. Remaining open to surprise, to data that doesn't fit our theories and observations that challenge our assumptions, may be the most important scientific attitude as we probe the mysteries of supermassive black holes. In the coming decades, as our theoretical models become more sophisticated and our observational capabilities more powerful, we may finally answer questions that have puzzled astronomers for generations. How do some supermassive black holes grow so quickly in the early universe? What determines whether a black hole launches powerful jets or remains relatively quiet? Could wormholes connect black holes across vast cosmic distances? The answers await us in the data gathering in observatories around the world and in the equations scrawled on whiteboards in university departments. This ongoing quest represents science at its most profound, pushing the boundaries of what we can observe, calculate, and imagine. In supermassive black holes, we confront the limits of our understanding, where the mathematics become so extreme that our best theories fail. Yet, in this very failure lies the promise of new insights, new frameworks, and new revelations about the fundamental nature of space, time, matter, and energy. As we stand on the threshold of this new era in black hole research, we can only imagine what wonders and surprises await us. The journey continues, propelled by human curiosity and ingenuity, reaching toward the ultimate nature of reality itself. And in this pursuit, we honor the true spirit of scientific inquiry, the recognition that each answer we find inevitably leads to deeper and more fascinating questions about our astonishing universe. As our journey through the fascinating world of supermassive black holes draws to a close, we find ourselves standing at the edge of human knowledge, gazing into abysses that seem to transcend time and space itself. These cosmic titans, lurking at the hearts of nearly every large galaxy we've observed, represent both the pinnacle of our scientific understanding and the frontier of what remains unknown. They are nature's ultimate laboratories, places where the known laws of physics are stretched to breaking point and beyond, challenging us to expand our comprehension of the universe's most fundamental workings. The legacy of supermassive black holes in shaping our universe is both profound and pervasive. These are not merely passive objects, sleeping giants hibernating at galactic centers. Rather, they are active architects of cosmic structure, their gravitational influence extending far beyond their immediate surroundings. The correlation between the mass of a supermassive black hole and the properties of its host galaxy, particularly the velocity dispersion of stars in the galaxy's bulge, speaks to a deep, co-evolutionary relationship that has unfolded over billions of years. This relationship reveals one of the most remarkable aspects of supermassive black holes. Despite containing only about 0.1% of a galaxy's mass, they somehow regulate the growth and evolution of entire stellar systems hundreds of thousands of light-years across. The energy released when these monsters feed, particularly in their active quasar phases, can heat interstellar gas, prevent it from cooling and collapsing to form new stars, and even eject vast amounts of material from the galaxy entirely. This process, known as feedback, represents one of nature's most spectacular examples of self-regulation. When a supermassive black hole consumes too much matter too quickly, the resulting energy output can effectively shut down further growth by disrupting the very feeding mechanism that sustains it. This balance between growth and self-limitation has played a crucial role in determining the properties of the galaxies we observe today, including our own Milky Way. Without supermassive black holes acting as cosmic thermostats, regulating star formation and galactic growth, our universe might look drastically different. Galaxies could have grown unchecked, consuming all available gas early in cosmic history. Stars might have formed in great bursts, rather than the steady, sustainable rates we observe in many galaxies today. The intergalactic medium, the vast, diffuse gas that fills the space between galaxies, would lack the heavy elements that supermassive black hole-powered outflows have spread throughout cosmic history. Even the largest structures in our universe, the cosmic web of galaxy clusters, filaments and voids, bear the influence of these behemoths. The enormous jets launched by some supermassive black holes can extend for millions of light-years, heating and stirring the intergalactic medium and influencing the subsequent formation and evolution of galaxies. These jets, moving at nearly the speed of light and carrying enough energy to outshine entire galaxies, represent some of the most powerful sustained processes in the known universe. Perhaps equally significant is the role that supermassive black holes have played in our intellectual history. Few cosmic objects have so captivated the human imagination or so challenged our understanding of physical reality. Black holes represent the ultimate enigma, regions where our current theories of physics make contradictory predictions and where the very nature of space, time, matter, and energy is called into question. The study of these objects has driven some of the most profound theoretical developments in modern physics. Albert Einstein's theory of general relativity predicted their existence, though Einstein himself doubted they could form in reality. Karl Schwarzschild derived the mathematical solution describing the simplest black holes while serving on the Russian front during World War I, finding beauty and order in the cosmos amid the chaos of human conflict. John Wheeler, who coined the term black hole in 1967, used these objects as conceptual laboratories for exploring the relationship between gravity and quantum mechanics. Stephen Hawking's discovery that black holes should theoretically emit radiation, now known as Hawking radiation, linked general relativity, quantum field theory, and thermodynamics in unexpected and profound ways. The information paradox, the question of whether information that falls into a black hole is truly lost or somehow preserved, continues to drive theoretical physics forward, inspiring new approaches like the holographic principle, which suggests that all the information contained in a volume of space can be represented on its boundary. This principle has led to groundbreaking insights, not just in astrophysics, but in condensed matter physics, quantum computation, and our fundamental understanding of entropy and information. In the public imagination, black holes have served as powerful metaphors and sources of wonder. They appear regularly in science fiction, representing both ultimate destruction and potential pathways to other universes or dimensions. The recent images captured by the Event Horizon Telescope have transformed these once purely theoretical objects into observed reality, allowing billions of people around the world to glimpse the shadow of the invisible. Our understanding of supermassive black holes also highlights humanity's extraordinary capacity for discovery. Consider that a mere century ago, Einstein had just published his theory of general relativity, and the existence of galaxies beyond our own was still being debated. The concept of black holes was largely mathematical curiosity, and the idea that objects millions or billions of times the mass of our Sun could exist at the centers of galaxies would have seemed like science fiction rather than scientific fact. Yet through the combination of theoretical insight, technological innovation, international collaboration, and remarkable persistence, we have not only confirmed the existence of these cosmic monsters, but begun to understand their formation, evolution, and profound influence on the universe around them. This progress speaks to the power of the scientific method and human curiosity to illuminate even the darkest corners of our cosmos. The technological developments spurred by our quest to understand black holes have had far-reaching implications. The sensitive radio receivers developed for astronomical observations have improved telecommunications technology. Computer algorithms created to process the faint signals from distant black holes have applications in medical imaging and data analysis. The precise timing systems required for the Event Horizon Telescope have enhanced global navigation and synchronization technologies. Even the fundamental mathematical and physical insights gained from studying black holes have found applications in seemingly unrelated fields. The techniques developed to model the complex, turbulent accretion flows around black holes have informed climate science and fluid dynamics. The information theories inspired by the black hole information paradox have influenced quantum computing research and data security. As we look to the future, supermassive black holes will continue to serve as cosmic laboratories for exploring the most extreme physics in the universe. The next generation of telescopes and gravitational wave detectors will allow us to witness the growth and evolution of these objects across cosmic time, from the universe's dawn to its present state. We may discover new classes of black holes, unexpected behaviors, or evidence that challenges our current understanding in fundamental ways. The ultimate fate of supermassive black holes, and indeed of black holes in general, remains one of the most profound questions in cosmology. According to Hawking's theory, all black holes should gradually evaporate through the emission of radiation, converting their enormous mass into energy over unimaginably long timescales. For stellar mass black holes, this process would take roughly 10 to the power of 67 years, trillions upon trillions of times longer than the current age of the universe. For supermassive black holes, the timeline extends even further to 10 to the power of 100 years or more. If this theory is correct, even the mightiest supermassive black holes will eventually dissolve, returning their mass energy to the universe in a final burst of radiation. This outcome connects to the larger question of the universe's ultimate fate, whether it will expand forever, gradually cooling and darkening, or perhaps experience some more exotic end. In either scenario, black holes represent some of the longest-lived structures in cosmic history, potentially outlasting stars, galaxies, and even atomic matter itself. The philosophical implications of supermassive black holes extend beyond physics and astronomy. These objects raise profound questions about the nature of time, the limits of knowledge, and our place in the cosmos. The fact that information apparently lost in a black hole might be preserved in subtle quantum correlations suggests that the universe maintains a kind of cosmic bookkeeping, that nothing is truly forgotten in the fundamental equations that govern reality. The extreme warping of space-time near a black hole's event horizon, where time itself appears to slow and eventually freeze from an outside observer's perspective, challenges our intuitive understanding of duration and simultaneity. It suggests that the passage of time is not absolute but relative, dependent on one's position in the gravitational landscape of the universe. What appears as a finite period to an observer far from a black hole could represent an eternity for matter approaching its event horizon. These cosmic monsters also humble us by highlighting the vastness of scales in our universe. The largest, supermassive black holes, with masses exceeding 10 billion suns, exist at one extreme of the cosmic scale, while fundamental particles like electrons and neutrinos occupy the other. That human consciousness, emerging from the complex interaction of atoms and molecules in our brains, can comprehend both these scales, from the subatomic to the supergalactic, represents one of the most remarkable features of our existence. Our journey with supermassive black holes also reminds us of the value of pure scientific inquiry. The practical applications of black hole research could not have been predicted when scientists first began exploring these theoretical curiosities. Yet the knowledge gained has enriched our technological capabilities, inspired generations of scientists and engineers, and deepened our appreciation for the universe's majesty and mystery. Moreover, this field exemplifies the international, collaborative nature of modern science at its best. The Event Horizon Telescope, which captured the first image of a black hole's shadow, required the coordination of radio telescopes across 4 continents, data processing facilities around the world, and the expertise of more than 200 scientists from 20 countries. In an age often marked by geopolitical division, such collaboration reminds us of our shared humanity and common curiosity about the cosmos we inhabit. As we continue to explore these cosmic enigmas, we do so not just with sophisticated instruments and mathematical models, but with the same sense of wonder that has driven human skygazers since our earliest ancestors looked up at the night sky. The poet William Blake wrote of seeing infinity in a grain of sand and eternity in an hour. In supermassive black holes, we encounter a similar paradox. Objects that, despite their enormous mass and volume, represent singularities, points where our current understanding of physics breaks down. That breakdown is not a failure, but an opportunity, a signpost pointing toward new physics and deeper understanding. Just as Newton's laws, which perfectly described everyday motion, needed expansion through Einstein's relativity to account for extreme speeds and gravity, so too may our current best theories require extension or revision to fully capture the physics of black holes. This recognition that our knowledge remains incomplete, that greater insights await discovery, embodies the true spirit of scientific inquiry. For the average person, far removed from the mathematical complexities of general relativity or the technical challenges of radio interferometry, supermassive black holes offer something equally valuable: perspective. In a human existence often preoccupied with immediate concerns and short-term thinking, contemplating objects that operate on scales of billions of years and light years provides a cosmic context for our brief lives. These cosmic leviathans remind us that we inhabit a universe of extraordinary wonder and complexity, one that existed long before human consciousness emerged and will continue long after our sun has exhausted its nuclear fuel. Yet rather than diminishing humanity's significance, this perspective heightens it. For in our ability to comprehend these distant, massive objects, to trace their formation and evolution across cosmic time, we demonstrate the remarkable capabilities of the human mind. As Carl Sagan poetically observed, we are star stuff contemplating star stuff. The universe evolved to become aware of itself. Through our study of supermassive black holes, we extend that awareness to the most extreme environments the cosmos has to offer, finding beauty and order even in these apparent abysses. The equations that describe black hole physics, the simulations that model their behavior, and the observations that confirm their existence represent some of humanity's greatest intellectual achievements. Looking ahead, each new discovery about supermassive black holes will likely raise as many questions as it answers. Each theoretical breakthrough will open new avenues for exploration. This continuous unfolding of knowledge, this endless quest to push beyond current understanding, epitomizes both the scientific enterprise and the human spirit. As we conclude our journey through the realm of supermassive black holes, we recognize that we stand not at an endpoint, but at a way station in humanity's ongoing relationship with these cosmic titans. Future generations will build upon our current knowledge, develop more powerful instruments and theories, and perhaps resolve mysteries that currently seem impenetrable. They will do so guided by the same curiosity, ingenuity, and sense of wonder that has driven all great scientific discovery. And in that continuity, the passing of knowledge from one generation to the next, each building upon what came before, we find perhaps the truest legacy of our exploration of supermassive black holes. Not just the facts and figures, the masses and accretion rates, but the ever-expanding horizon of human understanding, constantly pushing outward toward the unknown. In the shadow of these cosmic behemoths, we discover not just the extreme physics of warped spacetime, but reflections of our own quest for meaning and understanding. We find humility in their immense scale and power, inspiration in the elegance of the mathematics that describes them, and wonder in their role as cosmic architects, shaping the galaxies that give birth to stars, planets, and eventually, on at least one small world orbiting an ordinary star, life capable of comprehending these distant giants. The supermassive black holes that have been our focus throughout this journey are more than just fascinating objects of study. They are windows into the fundamental nature of our universe, teachers that challenge us to expand our thinking, and reminders of how much remains to be discovered. As we continue to observe, analyze, and theorize about these cosmic monsters, we participate in one of humanity's greatest adventures, the ongoing exploration of the universe and our place within it. And so, as we turn our gaze from these darkest of objects back to our bright, living world, we carry with us a deeper appreciation for the extraordinary cosmos in which we live. The mysteries of supermassive black holes, like all great scientific questions, remind us that wonder is not diminished by knowledge, but enhanced by it. Each answer reveals new questions. Each discovery illuminates new horizons. In this endless pursuit of understanding, we find one of the noblest expressions of the human spirit, a legacy worthy of the cosmic giants that have been our subject throughout this journey.